Good morning, Damir.
Hello, Yamin. Hi.
Hello.
Nice to see you.
Nice to see you too.
Yeah. How are you?
I'm okay.
Okay.
We're in home office.
Yeah. We are still working from the faculty. We have in generally direct classes, but more and more
Online
are transferred to the online. So I can expect that within next few maybe days or maybe week or two will also be completely at online education, because the numbers are not so good. We have a little improvement a few days ago, but now we are still on track.
Yeah, same thing here. Yeah.
Okay, you saw my answer to the Professor Holter. I will watch the situation, and I must make a decision at least 2 weeks before the mobility, because of my accommodation. I have to cancel it. Otherwise, they will charge me, I'm not sure, 10% or 30%.
Okay.
So I have to do it. So I will sign a contract with my university, and this contract includes also this virtual or online mobility. So I can do it also from Zagreb or from my home.
Okay. Yeah. So
those dates that are fixed with the students, I will be available on one way or the other.
Okay. Okay. Sounds good.
Yeah.
Yeah. Too bad, but that's what we have.
Yeah.
Yeah.
You have to wait for the better days.
Yeah. That's how it is.
Okay. Yeah. We will start in 2 minutes, but only 2 of us are here. I hope that guys are okay. Tomislav told me that Zoom automatically changed the time, because in sent schedule we had Greenwich time.
Yes. Yeah.
Not European, because Israt prepared this presentation.
Yeah.
This agenda. Okay, but
I send to my colleagues with the Central European time. They remind
just okay.
Yeah.
I saw it yesterday. I said, okay. Tomislav told me we will start at 10. I said, okay, how 10? It's written 9, but it's Greenwich time, not European, Central European. Hello, Julia.
Hello.
Hello. Can you hear us?
Yes.
Okay, thank you.
Hello, Julia.
Hello, Yamin.
So everybody is participating, right? All the institutions now.
Yes. Okay, I'll send you also on someone.
Oh, there is.
Hello.
Morning.
Morning, Israt.
Morning. How are you?
Pretty good.
We are okay. Yeah. How are you? Oh. Hello, Axel.
Hello, Damir.
Hello.
Can you hear me?
Hello, Israt. Are you with us?
Oh, she froze.
We had
she's back.
workshop on Monday, and there were a lot of problems with connection with Israt and Eugene. Hello, Israt. Can you hear me?
I mean, it's breaking up.
Yeah.
My line is breaking up. I don't know. You can hear me clearly or not?
Yes.
Now, yes.
Now,
yes. Yeah.
Okay. I can see my Wi-Fi is showing that you are connected to the internet, and it's fine. It's showing me the
I hope that everything will be okay. Otherwise, do you have recorded presentations from you and Dr. Eugene?
No, I mean, this time I didn't do a recorded one because last time it didn't run well. And yeah, so unfortunately not.
Okay. I hope that we will have a good connection.
Hopefully, yeah.
Yeah. So I think that maybe we can start because it's 10 o'clock.
Yep.
Okay. Okay. So I will just open my presentation. So, ladies and gentlemen, all participants, and as well as all the presenters of today's summer school, I would like to welcome you on behalf of Inex Adam project, under which this summer school was organized. The main idea is to present some topics regarding design for additive manufacturing, design for costs related to additive manufacturing, as well as development of materials for additive manufacturing. And I will show just at the beginning a few information. Tomislav, can you please enable my screen sharing? Thank you. So I will show just a few facts about the project. My apology for those who already saw this presentation, but I can presume that we have some of the new participants. So just a few facts about the Inex Adam project. The project started in 2018 year, and the plan for ending this project is next year, but we will see regarding this coronavirus, should we prolong a little bit the duration of the project. The total budget is a little bit less than 1 million euros, and University of Zagreb Faculty of Mechanical Engineering and Naval Architecture is the project coordinator. Here you can see the web page of our project. The main goal of this project is to get the knowledge for the researchers from Faculty of Mechanical Engineering and Naval Architecture from the field of design for additive manufacturing, some advanced knowledge from design for additive manufacturing and design of materials. And therefore, we decided to ask the best institutions from that field, from the Europe, to join us in the consortium of this project. And this is the situation of a consortium. We are small but quite compact and a good consortium from 5 institutions. Lund University from Sweden, Montana University from Austria, IDEMA Institute from Spain, from Valencia, and Brunel University, London, from United Kingdom. Those are our partners. There are some of the objectives of this project. We want to strengthen the synergy among the whole institutions, and maybe objective 2 is most important for us, is to gain more knowledge and to increase our innovation capacity in fields of advanced design for additive manufacturing and products and tooling, as well as medical modeling for additive manufacturing and material modeling for additive manufacturing. And of course, we would like to be more visible and increase our impact on a national as well as a regional area. There are a few work packages under the project, and for us the most important is this rising knowledge and excellence of advanced additive manufacturing. And there are a few moments from our education, because we visited most of the partners and learn a lot from about areas from the expertise of the partners. So these are some of the examples of development of material for FFF or FDM technologies from Montana University Leoben. The experts from Brunel University from London visited us in last June, in 2019, in June 2019, and transferred the knowledge about standardization of additive manufacturing as well as functional grade additive materials. You will see in a few presentations today the topics. Then we visited in September in 2019 IDEMA Institute in Spain and learned something about characterization and development of metallic materials for additive manufacturing, mainly for electron beam melting. And at the end, we visited at the beginning of November in 2019, Lund University, in order to gain some more knowledge about design for additive manufacturing, optimization for different criteria for additive manufacturing, like, for example, costs, which Axel will present you today. So, in today's summer school, you will see mainly a few information about metallic material development, mainly for electron beam melting, then design for additive manufacturing of metallic parts with some case studies from our partners from IDEMA Institute from Spain. Then you will see something about topology optimization and design for costs for additive manufacturing from our partners from Lund University. Then development of high field thermoplastics for additive manufacturing from our partners from Montana University from Leoben. And two topics are covered with our partners from Brunel University in London, and those are standards for additive manufacturing and functional graded additive manufacturing. And the last presentation is prepared from our side, but this is a presentation of possibility of application Altair software in optimization of designs for additive manufacturing, and our colleague Tomislav Breški will show you a few of the results. For all Croatian participants of this summer school, I just will share you the information that Tomislav is ambassador of Altair for Croatia. So if you have any further question about possible application of this software, please contact him and he will probably can help you or answer to your questions. In future activities, we will plan to organize a workshop for medical application and summer school for medical modeling for additive manufacturing. But as the situation with coronavirus is more serious, I'm not sure should we organize it at the end of this year, because the medical staff is more oriented nowadays on solving this problem with the coronavirus. And okay, we will be in touch with some of the organizations of the medical staff to see if there is any sense to organize this a workshop in summer school during this year, or maybe to wait the spring next year. Also, one of the very important activities is establishment of ADAM platform through which all the partners can provide a certain type of services to potential users of additive manufacturing from different type of sectors. And I want to point out that we also publish Advanced Additive Manufacturing Handbook with the topics that are covered from main research area from this project. So for any further question, you are free to contact me at my email. And this is enough for introduction, I should say, and we can proceed. We can proceed with our presenters today. And the first one, the first two presentations are coming from IDEMA Institute from Spain. The presenters are our Julia Urena Alcazar and Mario Martinez Ceniceros from IDEMA Institute Valencia. And they will show you some interesting things about metallic powders, their characterization for electron beam melting technology, as well as some interesting case studies with application of metallic powders in industrial projects in which IDM Institute was involved. So the floor is yours. I'm not sure who will be the first presenter, but please proceed. Thank you very much.
Yes, thank you, Dami. I will share the screen.
Julia, can you maybe just increase the volume because
it's okay now.
a little better. Okay, thank you.
Okay. I cannot share the screen.
Tomislav, please can allow
Yes.
all the participants sharing the screen.
Dami, you have to allow them as last week.
But how?
You are the host, so
I don't have any. All panelists. Okay. Julia, can you try that again?
Yes. Okay, now. And maybe, okay.
It's okay now?
Yes. Can you see the screen now? Yes. Okay.
Yeah, but the volume is still low, at least.
Yeah, okay, wait a moment, maybe.
Okay.
Can you hear me now better?
It's a little bit better, yeah.
A little bit? Okay, I will try. Okay, because it's not possible. Okay. Okay, now better?
Yeah, it's okay. We can hear you.
Okay.
Thank you.
Yeah, sorry. I will proceed now. Okay, so thank you, Dami, for the presentation. Good morning, everyone. My name is Julia Ureña, and today I will present you the topic of development of a copper chromium zirconium alloy by electron beam melting technology and the effect of the heat treatments on the material properties. So this copper alloy is a material precipitation and hardening with properties suitable for the nuclear fusion sector. And the materials for this kind of application is, the material properties is designed by ITER. ITER is the International Thermonuclear Experimental Reactor. It's an international research project. And this material is pretend to be part of a thermonuclear reactor. The material for this kind of application should present excellent mechanical properties and high thermal conductivity. So traditionally, this copper chromium zirconium alloy is processed by forging, casting, or hot rolling. But some challenges need to be faced, such as the coarsening of the chromium precipitates, heterogeneous microstructures, or complex geometries. So how about the additive manufacturing processing of this alloy? Will be feasible? So our approach in this job is the design and powder atomization of this material. This point is carried out by CEIT, which is another technological institute in the north of Spain, and they are expert in the powder atomization of different kind of materials. Then the additive manufacturing processing is conducted by IDIME, and the electron beam melting technology is selected, for example, in order to prevent the oxidation of the powder because of the processing under high vacuum, also because of the preheating of the material during the processing. But we need to our main challenges is related to the development of a new material by EBM. So can we get dense samples avoiding cracks and defects such as delamination? So we need to also study the influence of the heat treatments on the material performance, the material properties such as density, hardness, and thermal conductivity. So these topics are mainly the topics selected for this presentation. So first, I will show you results regarding the atomization of this powder. So powder with the composition according to the ITER specification has been produced. You can see the spherical particles with a particle size distribution suitable for the EBM technology. It can be observed the presence of some satellite, but this is being improved in the following atomizations. And regarding microstructure of the particles, we can see fine equiaxial grains. And we can see also the distribution of the chromium precipitates, which are mainly at the grain boundaries. So at this moment, 3 different atomization has been carried out. For this presentation, we selected powder with composition 1 and powder with composition 2, since the 3 is undergoing. And so mainly the difference between these 2 powders is the zirconium content. You can see here with the powder with composition 1% a low zirconium content according to the ITER specification, and the powder with composition number 2 a zirconium between the limit. So both of them showed a low oxygen content around 100 ppm, 150, and good values of flowability and apparent density. Apart from these powder properties, also the powder reactivity should be always tested before the EBM processing when working with an experimental material, since the powder reactivity depends on the composition, the size of particles, the humidity, morphology, also the method of powder production. So finally, this material is classified as non-combustible powder. And we selected powder with composition 1 and powder with composition 2 to produce square specimens, as you can see here, in a ARCAM system adapted for processing different kind of metallic materials, standard and novel ones. So, and the starting parameters was selected according to our knowledge related to the pure copper. So first, regarding with powder with composition 1 with low zirconium content, almost dense samples were obtained in the 9 samples. Only the porosity of sample 3, 6, and 9 was higher, probably due to an energy too high. Here is presented in this table the density values of all of the samples, and also the hardness in as-built condition and after heat treatment at a temperature of 400 degrees, 450 and 500 degrees. And you can see here sample number 1 present the highest level of density. Then regarding the hardness, all of them show values higher than the ITER specification, which is 128 beakers, even in as-built condition. And after the heat treatment, we can see that these values increase slightly for the temperature of 400 degrees, but at higher temperature, this hardness value started to decrease. And by same characterization, it's confirmed the abundant precipitation of the chromium nanoparticles, which are homogeneously distributed in the copper grains. You can see here on the left picture is a sample in as-built condition, and on the right after the heat treatment. So we can see stable microstructures without the coarsening of the precipitate after performing the heat treatments. So this is a good point, since we obtain a stable microstructure in both cases. With powder with composition 2, this is with a zirconium content higher respect to powder with composition 2, with composition 1. We can see here a higher porosity. However, sample number 1 and 2 present better level of density. We also think that this porosity is because of the low amount of powder, which this is being solved for the next atomization. We will receive bigger amount of powder, so we hope to achieve better properties. Here, regarding microstructures of chemically X samples, we can see the columnar shaped grain growing parallel to the build direction. And we can see here in details the precipitates with higher concentration at the beam boundaries. So despite of porosity, and that you can see here, it seems that the higher zirconium content play a key role in hardness, because all samples show a higher hardness respect to the powder with composition 1 and with low zirconium content. And also all of these values are above the specification of ITER. So apart of this, we can see also by means of the mappings, the EDS mapping, we can see a wide range of the precipitates not observed with powder composition 1. So we can see here different size of the precipitates, and mainly also located at the grain boundaries. Now we will see the relationship between hardness and density. Here you can see the sample, the powder with composition 1 on the left and powder with composition 2 on the right. So all the samples, as you can see, showed hardness values above the limit established by ITER. But also compared to the similar composition produced by casting or by traditional methods, similar microhardness values were obtained in the powder composition in samples processed with powder composition 1, and even higher with powder with composition 2. So it's important the zirconium content in the powder, since this results in better density and bigger size of these chromium-rich precipitates. And regarding the effect of the heat treatments, we can see that, as we saw in the previous slide, a selective heat treatment at 400 degrees with 3 hours slightly increase the hardness, but this not happens at temperatures higher than 400 degrees. And regarding the thermal conductivity, we can see here in generally samples with higher porosity, as can be seen here. As expected, the thermal conductivity was lower. But for example, the sample number 4, as we can see here, after the heat treatment, the thermal conductivity value is slightly higher compared to the value established by the ITER. So we can say that a specific heat treatment is effective in removing the defects from the copper matrix, and also the thermal conductivity can be improved by applying a heat treatment, and also the densification. And this is mainly attributed to the removal of the porosity and an improving of the precipitation of the chromium nanoparticles. So now we still continue with the development of bigger samples with a different batch of powder, and which we are trying to achieve better surface, as you can see, better quality of surface, as you can see here, and we are approaching to superior density in as build condition, and also after performing the heat treatment. So finally, as a conclusion, we can say that a copper chromium zirconium powder with composition according to the ITER specification and a particle size distribution suitable for the EBM has been produced. The zirconium content in the atomized powder seems to affect the quality of these samples. Higher zirconium content enhances the precipitation and the hardness of the samples. It has been achieved in dense samples by electron beam melting with an homogeneous microstructure and precipitation of the chromium nanoparticles. So we can say that it's feasible to process this alloy by additive manufacturing. And a suitable heat treatment can increase the hardness and the thermal conductivity due to this improving in the chromium precipitate and the removal of porosity and the atomization, and we are still continuing working in the atomization of a larger batch of powder together with the refinement, the improvement of the process parameters to achieve bigger samples. And this is all. Thank you for your attention. And
Thank you, Julia.
thank you.
Thank you very much for your interesting presentation. And I will ask Mario to continue with his presentation. Hello, Mario. We cannot hear you. Please unmute yourself, but you're not muted, as I can see. Something is not okay with the sound. You are muted now, okay? But we cannot hear you.
Hello, can you hear me now?
Now it's okay.
Okay. So live problems.
Okay, thank you.
Okay, do you see my screen?
Yeah, it's visible.
All right, so thank you, Damir and Isaac team for this for organizing this meeting. Good morning, everyone. My name is Mario Martinez, and today I will speak about the design methodologies that we can follow for the additive manufacturing, and some interesting considerations that we should bear in mind before facing these methods. So I would like to start my presentation with this sub-truth. This is an image that I found in LinkedIn some weeks ago, and it looks so interesting for me because sometimes people usually focus on the 3D printers, on how good they work, and all the features that they have. But sadly, we don't pay attention to the 3D printing, or to the design for the 3D printing, which is very important actually. So with my presentation, what I just want to transmit you is that the design for additive manufacturing is the key to unlock the additive manufacturing of this 3D printer. So with this presentation, my intention is to make this guy happier. Okay. So first of all, I would like to introduce a bit the differences between the conventional methods and the additive manufacturing methods, and this is the main reason why the design must be applied in a different way. So when we talk about metal processing, if it comes to material removal methods like milling, drilling, or so on, so basically in these processes we try to reduce the milling time and try to reduce to improve the life cycle of the tools. So basically what we try is to reduce the operations and therefore we increase the mass of the parts. So the less material I remove, the shorter the process will be in the conventional methods. Whereas if we speak about additive manufacturing, it's just the opposite. We are adding material layer by layer, and we have this design freedom that we talk about. So in this case, we try to reduce the additive manufacturing times, and therefore we try to reduce the material added layer by layer. So as a summary, we try to reduce the mass of the parts as contrary of the traditional method. So all in all, different processes, different design rules. We cannot manufacture a part which is processed by, which is designed for traditional methods in additive manufacturing. So the key point here is to identify what kind of applications will every manufacturing methods have. For instance, in casting forming, we speak about faster methods like injection molding and so on. As a drawback, we have to invest in a mold, but we will have high accuracy. So this is aimed to large productions. Okay. When we speak about material removal, about milling, drilling, and these operations, the process is lower than the casting and forming, but we have high accuracy and we don't have to invest in molds. We have more investments in tools and so on, but this is not such a high investment. So this is time to mid productions and high accuracy parts. And last but not least, when we speak about additive manufacturing, the process is slower than the casting and forming, but we can manufacture very complex parts without any kind of investment. We don't need molds in the case of plastic, if we talk about plastics. But we get this near net shape part that we call, so the accuracy is not as good as in the other processes. So, a summary: additive manufacturing is aimed to low productions and with high complexity. Okay. So, in order to focus the design for additive manufacturing, the first step is to identify what kind of parts from my production chains could have an added value if they are produced and designed for additive manufacturing. So here we can find a reduction in parts. If we have an assembly, we can join different parts to create a more complex part that reduces the parts of the assembly. We can reduce the cost. We can add new features to our parts or even customize our parts. We can reduce the weight. Additive manufacturing is a flexible process, so the reduction in the lead time is important if we compare with injection molding or with machining. But which is clear here is that additive manufacturing is not like a magic mouse, which is most of the people think. So basically, not everything can be manufactured by 3D printing. So additive manufacturing in the end is an alternative process that will not substitute the standard processes as machining or casting or injection molding, but will complement them. So when this first step, which is the part identification, is already done, we have to move forward to the second step, which is the technology and material selection. So for this reason, it is important, or is highly recommended, to have a solid understanding on how the technologies works and what kind of technologies can we find in the market nowadays. So parallel to this selection of the technology and material, to this combination, we have to reconsider our part. For instance, if I have designed a part made up of stainless steel, because I've always thought about the traditional methods, why this part is made of stainless steel? Maybe because I have not enough money to invest in a mold, but now with the additive manufacturing, there are new opportunities, let's say. So at this point, we have to reconsider why our part looks like I look. So, for instance, can my part be made of plastic? Well, questions like this that I have to ask myself. So at this point, we should define what technology and what material I will use to produce my parts, and then I can step to the next step, which is the part redesign. So before the part redesign, I have to bear in mind some key points before applying this design process. So regarding the part, we must understand the environment of my part, not just my part, but other mechanisms that will affect the function of my part during the life cycle. Okay. The other thing is that I have to understand the loads and constraints that the part should withstand. So before designing my part, it's like a designing process, but focus on the additive manufacturing. I have to understand the loads and constraints, and also the geometrical and dimensional tolerances to be achieved in my part. So regarding the process, it is advisable to have a good understanding on how the technology works, as I said, because depending on the technology, I will have some kind of limitations or some benefits that I will in the end apply to my design. So a summary, my design will be subjective to those limitations if I need support structures and so on. And regarding the cost, before doing all the process and start printing, we have to consider, or it's highly recommended to perform this quick cost assessment, just to make sure that, that the part will be economically feasible in the end. So how can I improve the process and reduce the cost of the additive manufacturing or the 3D printing processes? So the first key point will be the material reduction, as I said. Here we have much more flexibility than other processes. So the less material I put, the more economical the process will be. So this is an example of one of our projects, the scheme project, where this kind of bracket was redesigned from the first shape that you can see on the left, and the material was reduced by more than 80%. So this is one of the ideas: reduce the material of the part. The other one will be the well, we must pay attention to the nesting of this part in the build volume of my 3D printer. So let's say, for example, this part was designed for the multi-jet fusion, a process similar to the selective laser sintering. And here, we have a build volume, and the more parts we put in this build volume, the cheaper each part will be. So we have to try. We must try to increase the number of parts to be introduced in the build volume. This is a development we did for this coronavirus pandemic, and this is the typical face shield that you can see on the internet. So our approach was to modify these initial models that we could see on the internet up to this one, which is manufactured and folded. And once manufactured, due to the flexibility of the material, which is polyamide 12, this part can adapt to our head. And this is an interesting approach because we could increase the build volume quite a lot. The third point will be the reduction in the post-processing. So we have to pay attention in this point, because in some processes, both in metal and polymeric, after the part is manufactured, we have to remove powder, we have to clean the supports or remove the supports. And if we put some efforts in this step, we can reduce quite a lot the amount of supports and improve the part clean. This is an example, a project we did with Valverde, a company here in Valencia. And as you can see here, the left image shows these red areas which required support structures, and this was aimed to be manufactured in titanium 64 by IBM, by electron beam melting. And the redesign was to add these kind of geometries which allow us to reduce the superstructure almost to zero. So the fourth point will be to ease the quality control. So normally in additive manufacturing, we can see these very complex parts, and sometimes, occasionally, we can find that it is very difficult to quantify or to measure if our part needs some kind of dimensional tolerances and so on. So we have to think about these quality controls. In this case, the project was a precision FA, and the part was manufactured on a specific plate, which was located at a certain point, so we can measure where the different specs of our part are located after the part is manufactured. So regarding the different design for additive manufacturing methodologies, nowadays we can find these three options. The first one is the topology optimization. I think that our colleague Axel will move deep into this topic. The other one is generative design. This approach is normally uses specific softwares. Although nowadays we can find that the conventional 3D modeling softwares, as SolidWorks, CATIA, Siemens NX, are integrating these specific models to the modeling programs. And the third option is the CAD optimization, which is basically that you use the conventional tools that we normally manage to model these 3D models, so we can create optimized parts for additive manufacturing. I will not spend so much time here because Axel will explain us much better than me. So basically, we have here a simplified 3D model of the part as an input, which is the design volume. We put some loads and constraints, and the software suggests us some kind of shape that the mass is redistributed in the certain areas that will withstand the loads that we put in the first step in the inputs. So generative design is a groundbreaking method that is being used today. Here, basically, the designer or the engineer don't really design the part. So, I mean, they put the constraint and some design goals, and the software gives you a matrix of different alternatives where you can explore all the possible permutations of these solutions, and the designer can filters depending on the requirements, and then we can select this outcome as the one who best meets our needs. Okay, and the last one is the cut optimization. So basically here, if there is a redesign, we have a 3D model of a part that was initially conceived for other manufacturing process, and what we have to do is to optimize this part, bearing in mind the boundaries of the process and the part functionality, in order to improve what I was talking about, reducing material, reducing superstructures, and so on. So to our mind's experience and deep knowledge in additive manufacturing can make this option, the cut optimization, a very powerful tool. Just to show you an example of this cut optimization, this is a mixing valve. I will start from the first step. We have identified the benefits of this part if we manufacture it with IM. So this part was conceived to be manufactured in stainless steel and produced by milling. So what are the advantages of additive manufacturing here? We can reduce the weight of this part because it is attached to a robot. So any reduction in weight will improve the behavior of the part and the performance. We can improve the behavior of the internal channels. So basically, when we speak about milling, we can only perform straight weight drills. So the connections between these internal channels are 90 degrees. Yeah, just the fluid connection in this internal channel is not as optimized as it could be in additive manufacturing. And maybe we can reduce the production cost based on the first economical step. So the second step is understand the part and its environment. So here we can identify the different joining points that we have, some screws to attach this valve to a plate, and some guns that we have to put to insert in these holes. Okay. We have to understand everything around this part, not only the part. Well, once we have identified the technology and the design restrictions, in this case, we decided to focus on the multi-jet fusion because based on previous experiences with such a low load, which is 30 kilograms, multi-jet fusion can be a good approach. So in this case, we don't have superstructures, we have to optimize the material, and we have to optimize the part nesting. There is not machining requirements for this part at this point. So we have identified here, highlighted in red, the surfaces or the specs of our part that should be kept. The rest of the part, this white box, can be redesigned. So at this point, we start optimizing the part. You can see here that this connection, this internal connection, was very optimized for the additive manufacturing. We compare them with the milling. And well, we started creating the part from the inner skin. Then we give thickness, and we included this nut housing for the attachment of the guns and the screws, because multi-jet fusion can perform functional screws. So at this point, we took some decisions about using shorter screws like this M6/16 instead of 60 millimeters in length screws. So this is a good improvement for the part and for the weight of the screws. And last step will be to calculate the numbers of our optimization and to test it in real conditions. So as you can see here, the weight was reduced by 97%. Nowadays it's manufactured in polyamide 12, so costs have been highly reduced too. And just to end, I will not spend so much time. I just wanted to show you some important cases that we have developed here in IDME. These two are developed within this COVID situation. The first one is a connection for the Decathlon health masks that you maybe, I guess that you already know. And the second one is a machine that was developed, was called Aire 19, and basically it's a ventilation system for the coronavirus affected persons. So some parts of this equipment were manufactured and optimized for the process. On the picture on the top of the slides, we can see a very interesting case. This is a hybrid approach where we mixed metallic parts that you can see on the right side, which gives the part the structural strength. And afterwards, we cover these titanium parts with a vacuum casting resin. So in the end, we have this product which is reinforced by means of this internal structure made up of titanium 6. Other some interesting cases are these applied to the automotive sector. This is a kind of mask to test the assembly of the back panel of the car, and the approach of this piece was to, well, you know that this is a very big part, so we have to put them and reinforce some kind of aspect of the part. We have to put them in more than 20 parts that were glued afterwards, so that in the end you can see here it's a bit difficult to see, but once glued we can test it on the back side of the car. Some other applications in the automotive sector. These are some structures that are used to move the blocks of the engine of the cars that were manufactured by milling with a high cost, and actually they are using multi-jet fusion with this polyamide part to manufacture these tools. The other one is a cover for the crankshaft of the vehicles. It's quite similar to the face shield that I showed previously. Basically, the approach here was to design this part unfolded, and afterwards we can fold it and we can fold the piece and clip them in just to protect this crankshaft. Other application in the automotive sector is this kind of cap for the batteries. Actually, there was a problem here because in the production line there was a camera that detects this red color, and the option here, instead of doing a mold and investing in such a mold, was so they decided to manufacture this part by additive manufacturing. So you can see here how the build platform look like. So as you can see here, we try to improve the nestability of the parts. And again, with the same example, these are some structures to create these isolating spaces in the different workshops for the automotive sector. So again, they use the additive manufacturing because the lead time was much better than if we start creating this mold. Some others, this is an oil injection valve that was optimized from this first step to this one. And as you can see here, there were several optimizations. The first one you can see here that has some kind of supports, but in the end, with some kind of readjustments of the geometry, we could achieve a support zero part. So here, basically, the post processes were reduced up to 0. Some iron nozzles for painting that were manufactured by metal alloys, and well, some other parts. These were induction coils for hardening for a company, GH Induction, that they are actually applying these design rules for creating these complex channels with internal geometries. This one was already presented, and this is a robotic arm manufactured in titanium 6-4. And the interesting point here is that the arm was also optimized in order to conduct all these movements through the inner skin of the parts. So all in all, and as a summary, what I wanted to transmit is that we have to make this guy happier. We have to pay attention in the design for 3D printing, because there is no point in keep designing for other processes and manufacture by 3D printing. There is no sense. So I hope that that you enjoy the presentation. Thank you all for your attention. Thank you.
Thank you, Mario, for your interesting presentation and a lot of interesting projects that can maybe motivate all the participants to think maybe on a little bit different way on the design of parts. And I can agree with you with this slide, last slide, completely. Although we have in our agenda the time for questions and answers at the end of today's summer school, but maybe it's more easier to put a question right as you have the need to have a question, and write it down in question and answer area, and I will then ask the presenters to answer to the questions. So if you have questions for first two presenters, please do not hesitate to write it down in the question and answer section. And we have already one question for Julia, and Israt put a question regarding ABM heat treatment and thermal conductivity. So the question is, how can you optimize the building strategy parameters to achieve both hardness and thermal conductivity? So Julia, can you please answer to Israt? Thank you.
Yes. Yeah, it's a good question, because first we need to reach a compromise according to the zirconium content. So this is our first experiments with two different powders. So we understand that the zirconium content is an important element which affect the hardness and also the thermal conductivity. So I think we need to achieve a compromise in the chemical composition, and then achieve a high level of density. So our strategy for the parameters is has to be focused on this, on achieve almost near almost the 99%, and then selected the ineffective heat treatment, which we can see that is around 400 degrees, 450. So yes, our main point, I think, is to find an exact, right chemical composition, and then achieve a high level of density. So in that way, after performing the heat treatment and also the or heat hot isostatic pressure, I think the properties will be the most desirable.
Thank you, Julia, for your answering. I hope that this is satisfied with the answer. And as I can see that we do not have any further question from the audience, I will announce the next two presenters. We will have two, although we have in agenda just Axel, but we have also one the new panelist. It's Jože Tavčar. And we have two topics. The first one is topology optimization, and probably Axel will present this topology optimization for additive manufacturing. And then Jože Tavčar will present us a design for costs in relation to additive manufacturing. So Axel, please, can you proceed with your presentation? Thank you.
Yes, thank you for the introduction, Damir. I'll let Jože begin with his presentation about general design for costs for additive manufacturing, and then I'll jump in and talk more specifically about topology optimization. So I believe you can jump right in and...
Yes. So hello to everybody. I have joined Lund University recently. Originally, I'm coming from Ljubljana University. I will start sharing the presentation. So the topic is cost calculation, and I will continue in some way what has already has been presented. Before I start, I would like to present some typical cases of additive manufacturing applications. So the first one is rapid prototyping, but at rapid prototyping, we have only few samples and we optimize the product for the serial production. So in this case, the costs are not so urgent. Therefore, it was also the first case when additive manufacturing has been successfully applied. The next type is application for the small batch production, and it's already competitive in some cases. And this is where cost is typical parameters, while we have several products where we can produce them with some 100 pieces, and the traditional methods of manufacturing are not competitive to additive manufacturing. A special case are some special tools like for injection molding, and in this case we actually with new function we improve the process, and therefore such application have high added value. And also we have customized products, for example in the implants, rehabilitations, where we also have high added value, and it's already nowadays competitive. So our idea is to make a simple tool that can assess the costs already in the initial phase, in the conceptual phase of design. So it's really very important. We have already heard that product design has the main impact on the cost, and therefore this cost awareness need to be pushed backward to the conceptual phase. While additive manufacturing is not a cheap technology, therefore it's very important that we understand this break-even point, and to make the right decision when we decide about the way of production. So the idea is to have some basic input data that is available already in the conceptual phase of the product development, and on the base of this, such as volume, material, processing technology of additive manufacturing, quality range, then then we have the output data that help us to guide us. Do we have competitive product, or do we need to do some upgrade? So there can be maybe opposite opinion. We have already each 3D printer has software like as Ultimaker Cura. We can precisely calculate the costs and also processing time, but we would like to push it backward to the conceptual phase. When we can apply such software, we already need a 3D model, but we would like to do this cost awareness a step before. Let's just mention also the very popular diagram from the cost efficient design book. So if we want to have influence, we need to take decision as soon as possible. So in that phase, we have flexibility to reduce the cost, to optimize processing, and therefore it's important to have this awareness. In the conceptual phase, we don't have available all the information, therefore we can do some mistake, but it's acceptable. The most important is that we go into the right way, that we are aware what is design and processing options for improvement. So actually, this diagram is very similar as we have already seen today. If we want to do cost calculations, we need to do the design optimization first, and also we need to check if the technology fit the technical characteristic. And later, then we do calculation, but we can repeat this several times. So important is that we optimize the product in the right way, and that we have this cost awareness all the time. So I'm not wasting time about the design for additive manufacturing. We have already seen a nice presentation. I will just go forward. We have also heard that it's important that the product that is going to be manufactured, that the mechanical properties fit, that the material temperature range is fine. So the not each technology is appropriate, but we will see later that it's the selection of the technology has very important influence also on the cost. So we need to select that one with still fulfill the requests, and that is the cheapest one. While for example, the extrusion technology has some limitations, and we need to be aware this already at designing and later when we are selecting the process technology. So here again some criteria. We have maybe already heard more detailed criteria, so it's important that the selected technology guarantee the roughness, tensile strength. Important is what's the level of isotropy, and also if the cost and building time are acceptable for us. So let's repeat once again. We would like to, in the conceptual phase, input the data with a simple internet application. We will that has all the basic information about the available processing technologies. We would like to assess the costs, and at this time with the structured cost, we would also like to get the guidelines how to do redesign if it's necessary, and then to repeat this iteration several times. Before we go further on some examples, I would like to stress again that beside the manufacturing cost, we have also total costs and lifetime costs. Let's see on the example. If we have a simple product, actually the manufacturing costs are the dominant one, but in some applications, it's actually more important if we improve the efficiency while we reduce the lifespan costs. We reduce the operation cost, and as an example is the tools for injection molding. We will see that we improve the efficiency, we reduce the production cycle, and it's very important what is actually adding value to the additive manufacturing. We should be aware that the cost structure include material costs, operators costs. So we need to buy the machine, we need to have the place, and if even we don't use the place, we have some overhead costs. So we should be aware what is the structure of the costs. While this is also when we are optimizing the product for the cost, we have then here the potential where we can reduce the costs. And let's now explain this with some examples, with numbers. So especially the metal additive manufacturing can be quite expensive. So if we pay back the machine in 2 years, and the cost of machine can be over €1 million, and that means if we take an average, we have for 1 hour of processing, we have the cost of €65. And that means if we take not the most complex, but an average part, that can take about 100 hours. We should be aware that the single part cost already €6,500. And we should ask ourselves, can we afford it? Can we use another technology? Beside the processing cost on the machine, we have also pre and post processing, and this part now already costs, if we add 45% to the printing costs, that means we are already at €12,000. What is actually the cost of a car? And we really need to be aware of these numbers, and we need to take the right decision as soon as possible. So here we have a similar example as we have seen before, but just the initial design is adapted for drilling, and reproduction of this design would be very expensive. So it's €15,000. With a modification of design, we come then to the cost that is only €2,000. This is so over 7 times difference, and this difference, we should use this potential every time when we are applying additive manufacturing. There is another example. So the cooling channel at the injection molding. So in traditional way, we can drill them straightforward, so we are limited. But with additive manufacturing, we can apply this cooling channel closer to the part to make this cooling more efficient. And in this example, so the cycle time of injection molding was reduced for 33%. It is significant, but we should be aware that we cover this investment with this improved tool design if we produced 66,000 parts. So it is quite a high number, but in some cases not, but we should be aware. We should have these numbers in our head when we are taking decision. So shall we apply the additive manufacturing or not for tool design? So just a few examples for this part. It is produced 2.4 hours, and the break-even point is, if we compare it with the injection molding, is about 200 parts. But we shall be aware that the cost of materials, the processing is getting cheaper, especially for the polymer materials. So let's put this. So it is the housing of the Raspberry Pi, a cheap computer, and many enthusiasts have tried to print this. It is not so demanding a part from the geometry point of view, so we can apply extrusion technology. The volume is 64 cubic centimeters, and the cost of this part is, on one side we have the material cost, 1.6 euro. Then we have processing cost, so the machine is not expensive. We put here that processing cost is 6 euro. And for pre and post processing, so we said we need 20 minutes. And for this, it's actually the most expensive part. It's 9 euro. That means this part costs almost 17 euro. So if we compare this with the injection molding, so for injection molding, we need to design the tool. It is quite expensive. So the cost for a simple tool that is opening just in one direction, it's estimated for 10,000 euro. And if we need to split this high cost to 20 pieces, then we see that the cost of tool is very significant. The part costs more than 500 euro. But if we have the high volume production over 100,000 pieces, then we can see that the cost of tool is only 0.1 euro, and the operator and the material cost dominate in this case. So we should be aware that, for example, in this case, the break-even point is 60 parts. So if we produce them by additive manufacturer, it's cheaper. But if we have higher numbers, it's better to do it by injection molding. But we have also some other way of manufacturing. It is just for comparison. So this calculation is also important if we are just, we have seen this before, but if we are just selecting the technology, we should be aware about the volume, mechanical properties, and temperature range. And this simple help us to select the right technology that fit the, and also to have at the same time comparison between the costs. So I just would like to repeat for the end, we should be aware that cost is determined already during the product design and the processing technology. So these 3-4 things should be considered concurrently, and in this way we will apply the technology, the additive manufacturing technology, in the right way and have also competitive products. So we have tried to summarize some basic technology to compare the prices. So the data is changing. This is just for the overview. I would like to stress that the costs of the different technology is very different. We should consider in the beginning, in the conceptual phase of the product. So the time is over. Just to finish. So the point is, the message is, push this cost awareness early to the design phase, while the design for additive manufacturing is a must. And by applying it in a proper way, we can have also competitive products. So the idea is to have a simple internet applications where it's also possible to do this calculation in a user-friendly way, and also to update regularly the information about the materials and processing technologies. And now a step forward will be done by Axel. He will present the possibilities for the product optimization.
Maybe before Axel proceed, we have one question for you.
Yes.
Maybe. Now another question. We have two questions for you. In a question and an answer form. Probably you can see it, but I can read it. Regarding the first question is regarding the selection of additive manufacturing technology beforehand for a specific application. It might happen that one technology results in better mechanical properties or surface finish compared to the other one, but it's costlier. So how do you take this into account? This is the first question.
So therefore, it's important that we are aware about the processing technology. Maybe we have, if we are still in the design, it's too late to do calculations when we are in front of the selected machine. So we should do these calculations already in the design phase, and we maybe, if we can see, okay, we can apply a better machine, we get better mechanical properties, and we can reduce the size of the design. So if we consider this concurrently, we can optimize the product also to consider the function and the available processing technologies.
Okay, thank you. We have two more questions. Second one is, will the cost of additive manufacturing always remain constant as indicated by the diagram that you have shown us? And if not, how will it affect the cost consideration? For example, if in some cases the costs for additive manufacturing is not constant.
So actually, it is a simplified model. But the fact is that the process of adding material, it's relatively slow, and so if we have just a few parts to manufacture, then of course this trial, this setting up, it take time, and definitely few parts are more expensive than if we optimize the technology. We already know all the parameters, but also it's very important how we set up. So if we make at the same time more parts, we can optimize how is this configuration on the 3D printing machine. So definitely it is a simplified model, this a straight line, but it is not far away from the truth. So we can optimize it, but in limited way. So if we have a high volume production, definitely the additive manufacturing is not the right way, but it's for the small batch productions, for customized production, and in this way we can be competitive.
Okay, thank you. And the last question is, which 3D printer did you use for comparison for price on slide before conclusion? It's one of the before conclusion.
Maybe this one?
I'm not sure. Maybe you have this table. Yeah, you have a table at the end.
So the requests were not, there is no high demand. So the 3D printer for the cost of few thousand euro can be applicable for this case. So it was taken as example, but we also have printed a bit different design, but it's just an example. we have relatively low technical demands, so therefore we can use the cheapest processing technology. And the information, the point here is the structure of the costs and comparison with the injection molding.
Okay, the question was on the table a few slides later, 2 slides maybe after this. Can you go?
Maybe this comparison?
I'm not sure if this one was the question. Okay.
So these informations, we actually cannot compare extrusion in general. Each machine has different properties, has actually this need to be done on the level of the machine. But it is to have an overview. If we would include all details, then we cannot show this on one table. But the point is, processing technology has significant influence on the technical characteristic of the object and also on the costs. And we should consider this when we are designing the product and select and taking decision about the processing.
Okay, thank you very much for your answers, and thank you audience for putting questions. And now maybe Axel, you can proceed because we don't have any further question to.
All right, yeah. I'll share my screen.
Axel?
Yes. See, you can hear me? Yeah. Okay, thank you for that. As we just heard about time for cost within additive manufacturing, a natural part of that is, of course, to reduce the volume of the part being printed. Therefore, I'm going to be talking about topology optimization in my short presentation here. And I'll note that topology optimization here is not just for lightweight, that is to save weight for space applications or flight applications. It's also for just reducing the volume of whatever is being printed. Because as we just saw, a major driver for the cost is really the time it takes to print the parts. So the volume being printed, the volume being melted in a metal machine will, of course, strongly affect the part cost in the end, even though you might not be looking at the part as something that you would typically want to make as light as possible. So that's the reason for talking about that here. My background, just shortly, is that I'm a senior lecturer at Lund University at Product Development, Design Sciences. And I do mainly research within generative design of different types, not only within additive manufacturing, but also within other manufacturing technologies. Also looking quite a bit into mass customization, that sort of thing. And at Lund, we have a fairly full-fledged lab. We have access to a number of different types of printers and technologies. So metal machines and polymer machines, etc. But this talk right here is going to be about topology optimization. And before we jump into that, just as we've seen previously, we have to talk about the reality of metal additive manufacturing. And the reality is that it's expensive and that it's time-consuming to print it, and it's time-consuming to post-process it. So you really have to have a good reason to make a metal AM part. And typically what we say is that if you haven't specifically designed a part for a metal AM, it's probably not worth using AM for producing it. And principally, this is due to the need for support structures and the amount of post-processing that we need, apart from the fact that it's a fairly expensive process in itself. Obviously, as we've seen before, one of the major advantages of AM is that complexity is free. We can print something that's highly complicated without it in principle costing any more than printing something that's quite simple. So for instance, this guitar example from our previous professor, Olaf Diegel, is a good look at it. If we print the guitar to the left, it's probably a good idea because it's very complicated. It's got lots of details, whereas the guitar on the right, it's very simple. It's probably more suited to other manufacturing methods instead. So this complexity for free we can use for many different things, not only making guitars, but also making things lightweight. And that's really what we're looking at here with topology optimization. Now, topology optimization itself is in principle just a way method for redistributing or removing as much material as possible from a part, given some certain constraints and objectives about what sort of mechanical properties that we need. And for this, we have to run some sort of finite element analysis, and then based on the algorithm, we can redistribute or remove material. And this has been around for quite a long time, at least 30 years or so, so it's almost the same age as AM. But previously, we haven't seen that much use of it because of the nature of the shapes that we get out of the algorithm, which are typically quite geometrically complex. And those are not always suited to more traditional manufacturing methods. So just to contrast topology optimization to some other optimization methods that might be more commonly available in software packages, etc., at least up until a couple of years ago, we can look at topology optimization as a sort of good starting point for conceptual design. It works on the whole design space. It gives you a rough idea about where material should be placed. However, on the downsides, typically the results need to be remodeled in some way. And typically you have to do this, at least to some extent, manually. Another downside is that we're quite limited in terms of different goal functions or objectives and constraints that we can use. And this is compared to traditional, you might say, parametric optimization that works directly on a CAD model, for instance, and can change the dimensions of this CAD model. And thereby the result, the end result that you get from this type of optimization is also a fully defined CAD model. So this can be sent directly to manufacturing, basically. So you don't have to spend any time manually remodeling it. And we are very flexible in terms of the goal functions that we can use. And so basically, as long as you can measure it or you can calculate it, you can use it for parametric optimization. Whereas for topology optimization, we're a little bit more limited. This is the basic workflow for topology optimization. We start off with a design space, so the design space within which the algorithm or software can redistribute material. And typically, you want this to be as big as possible. The bigger it is, the larger potential you have to find an optimal load path. After that, we add on constraints, mechanical loads, or other types of boundary conditions, depending on the type of analysis you're doing. And we also define areas where we want to keep material. So typically, where we have our boundary conditions, or for instance, fastness, etc. After that, our algorithm is run and spit out some sort of result. And typically, you get a result that looks similar to this in red here. So it's a fairly noisy, quite messy type of mesh-based result. And even though we're using additive manufacturing, typically you want to do some sort of modification to this result, to this mesh, to be able to actually print it and to use it as intended. So that's the next step, reinterpreting the results, and then finally validating and manufacturing it. So that's the basic workflow here. And I hope this will show up, but this is simple two-dimensional topology optimization to see how the algorithm can redistribute material very quickly and efficiently based on the load situations and constraints that we set up. Now, in two dimensions, this is obviously very fast. You can run this on your iPad or Android phone or whatever you have. However, in 3 dimensions, this is quite a bit slower. So you have to keep things a little bit more constrained. So I'm going to give you a couple of examples of different applications of this, not only our own, but also from other researchers. So this example you might have seen before, the antenna support structure that was redesigned using topology optimization from a basic design space, adding supports and loads on it, reinterpreting the design, and then finally validating this design and manufacturing it. And when this was manufactured, I believe it was one of the largest things printed at that point. Now, this antenna support is for Earth orbiting satellite, so it needs to go up in space. And I think each kilogram that you send up into space costs something like $20,000 or thereabouts. Obviously, you want to reduce the weight as much as possible here. And then using topology optimization, they were able to reduce the weight by 50% with thereabouts, while keeping the stiffness and mechanical properties of this part constant. So that's quite a cost saving for this particular application. However, we can use topology optimization not only for structural applications. And there is a lot of research going on into other domains as well. It's like this example here with topology optimization of passive heat sinks. So heat sinks are typically looking something like this, where we dissipate heat using fin structures that have a large surface area to conduct heat away using convection. But we can set up this problem for topology optimization to try to maximize the convective heat transfer within a certain design volume. And this actually generates some, again, very organic, complicated structures, almost looking like something that you'd find beneath the ocean, for instance. Another application is actually within fluid dynamics. And this example is topology optimization of a fixed fluid diode. So the fluid diode works in a principle that's similar to a regular diode, in that it allows fluid flow in one direction, whereas it stops the fluid flow in the other direction, or almost at least. So we can set this up as a topology optimization problem to enable flow in one direction, to have a low pressure drop in one direction from left to right here, whereas in the other direction we have a high pressure drop due to all these recirculation points and cavities, etc. So you should be aware that even though most of our applications are within the structural domain, there are useful areas for topology optimization with heat transfer and fluid dynamics as well. But to give you some sort of methodology for topology optimization, first thing to note is that as with any type of analysis, you have to know exactly what sort of boundary conditions that your part will be subject to. What kind of loads will they be subject to? What sort of supports will they have? Because if you don't do that, then the result that you get in the end will be quite meaningless. So garbage in equals garbage out in this particular case. So that's important to keep that in mind when looking at your setup and analysis tools. And the other thing is that one of the downsides here that I mentioned previously is that it's not really a process that automatically produces ready-to-use models. It produces rough models that really need to be reinterpreted in some way. And there are a couple of different approaches to this, but the overall goal is to go from a rough mesh-based result like this into something that is manufacturable and that have all the requisite spaces for fasteners, etc., for instance. General thought process here is to begin by simplifying the model to create the largest possible design space. Really want to give the algorithm the best possible chance of finding the optimal load paths in this particular case. So one shouldn't really be limiting this to existing design. You should be using something that's even larger in terms of design space. And the next part is to set up your load cases. And setting up load cases here, typically you want to try to divide your load cases into loads that will happen at the same time. So if your design will have to endure loads that happen at different points in time, loading in different directions, etc., you typically want to divide those up into different load cases or scenarios. And then these load cases will combine into one single optimal design in the end. The next part is to try and decide how to smooth the model, as I talked about before. And there are a couple of different approaches. The first one is obviously to re-CAD the design. So to start from scratch in CAD. And this is of course quite time consuming, but on the other hand, you end up with a fully defined CAD model that you can easily modify and update later on. The other possible way is to use operations directly on the result mesh. So you can use different software and algorithms to smooth the mesh, to just smooth these rough edges out. And this is of course quick and quite robust, but on the other hand, you end up with a low quality mesh and you have basically no parametric control of this. Sort of in between approach is to use different types of polyNURBS surfaces to wrap around your result mesh. And this gives smoother results. It gives you a little bit of control, but you get very complicated organic surfaces that are quite difficult to manipulate later on. So the amount of parametric control is still a little bit limited. Our third option is to use lattice-based design. So basically to use different type of lattice structures to represent the topology optimization result. And something that one can see here in this example, for instance, where we have, this is not actually manufactured using AM, it's rather investment costed. But you can see how in this case, using different sized lattices and different thicknesses of lattice in this airframe sheet, one can increase the thickness in areas where we have high loads and high stresses, whereas others we have quite a thin mesh here, while keeping the outside with a fairly well-defined, easily parametrically manipulable contour here. So we keep all the complexity on the inside. This is an approach that I think is quite a useful way, is that we begin with the topology optimization and use that to create a simplified CAD model, and then use lattice-based design optimization or topology optimization to create this complicated inside of the structure instead. But of course, this might seem easy. You run a topology optimization, you get your results, and then you can print them. But of course, as we've seen before, a lot of the effort that's spent with especially metal AM is after the print has finished, and that is in post-processing. And this is in principle due to the support material that we have to use to conduct heat away and to support the structure while it's being printed. So in this case, for instance, in this guitar, you can see the support structures down here. You can see that there are a lot of support structures that need to be removed. And if one adds the times up here, one gets maybe 1 or 2 days spent printing and preparing the print of this guitar, whereas perhaps 8 days just in post-processing. So post-processing is very time-consuming and expensive, and that means that we want to be able to optimize for it as well. So that's possible in a number of different softwares today. We can optimize different build orientations, for instance, and get results in that minimizes the amount of post-processing, basically. But to summarize here, I'm trying to keep within the allotted time here, is that even though we get some really cool looking results and we get some interesting lattices, etc., from topology optimization, it's quite quite a straightforward process these days with the softwares. One should be aware that within topology optimization, within these softwares, the stresses are not always particularly reliable. So one really always wants to validate these designs in one way or another. So for instance, in these results here from Inspire, one can see that we have some fairly bad looking stress concentrations that would definitely not be allowable for cyclic loading and within fatigue applications and so on. So I guess the end message here is that while complexity is for free when it comes to manufacturing the parts, complexity certainly isn't for free in terms of designing and analyzing and validating these designs. So when we are still at a point where validation using different virtual methods is a little bit tricky and time consuming, and one should be aware of this when using topology optimization and lattice-based optimization within AM. But there is a lot of work being done within this field, so I'm sure within the next couple of years we'll see some really interesting approaches to solving this sort of complexity problem for us. All right, so that was my presentation. I'm not sure if we have time for some questions as well.
Thank you, Axel, for your presentation. And we have 2 questions so far. Okay, we have 3 questions now.
Right.
The first question is, what is the name of the software used to compute in real time the 2D load path?
Oh, this is a software called TopOpt. It's from the Technical University in Denmark, so from DTU.
Mm-hmm. Probably the last question is also, which was that tool by DTU?
Yeah.
the same question.
Topology optimization. If you search for it in the App Store or online, you'll find it.
Okay. And you, asks in the aircraft seat with the lattice structure, what does it mean 1 kilo is equal to 200 million US dollars? It's for 600 and something seats per aircraft, I should say.
Yeah, exactly. That's a little bit of a overestimation, I think. It's an estimation of how much you save by reducing the weight of one aircraft seat by 1 kilogram. But that's calculated across the entire airplane and across all airplanes in their fleet and across the lifespan of the fleet.
It's 100 airplanes. It's the largest Airbus, A380, and along during the life cycle of the aircraft, it's 20 years. Yeah. So you can expect that amount of savings regarding the cost for the fuel. So it's 600 and something seats for largest Airbus.
Yep.
I hope that Yomin is satisfied with the answer. Yeah. Okay. Thank you, Axel. And Yomin is the next presenter before the break. The title is Development of High-Field Thermoplastic for the Material Extrusion for Additive Manufacturing of Metals and Ceramics. So, Yomin, please, can you proceed? Thank you.
Thank you, Damir. I will just share my screen now. Okay. Okay, so welcome everyone, and thank you, Dami, for the introduction. So I will switch a bit back again into the materials for additive manufacturing that it was started with Julia, but in my case, I will be talking about some composites materials, which we name highly filled thermoplastics. And these are used for material extrusion for the manufacturing of metals and ceramic components. So the learning objectives of this talk is to give you an overview of the additive manufacturing methods for metals and ceramics. And then I will put a bigger emphasis on the material extrusion of metals and ceramics. Then we have to discuss the strengths and limitations of using these technologies for making metals and ceramics, and how can we develop materials for this technology, because it's a quite complicated process. And finally, I give you some examples of how these parts that are made by material extrusion can be applicable. So this is an overview of all the additive manufacturing technologies available at the moment. It's a generalized overview and uses the terminology defined in the standards currently. One important notice is that all of them can be used to produce metals and ceramics. Not all of them directly, but some of them are indirectly. And this is what is shown in this diagram here. So the only blue part here is a direct production of metal parts in this case. So you have different feedstocks from powder, wire, sheets, rods. And then you have this green section here, which is the indirect production of metal parts. In this case, you use, for example, dispersions on suspensions or paste, filaments, pellets, or you can also use powder. So as you can see, there is many different technologies because there's a lot of clever people out there and they have come up with different ways to build the parts. So the most common method of producing metal parts is actually powder bed fusion, and this was already discussed by Julia. And the typical name for this is selective laser melting, which is done with a laser, of course. And then you have selective laser sintering, which uses used for coated powders, for example, and electron beam melting that Julia was discussing before. So this is a schematic of the electron beam melting, similar to electrical electron microscope. The materials that you have to use for this kind of technology have to be free-flowing powders, and they have to have, therefore, a specific particle size and a specific geometry, right? So you can attain this with many different metals and alloys, and you can also have coated ceramics so you can build ceramic parts out of it. These are just examples of photos of laser melting technology with 4 lasers building simultaneously 4 different parts at the same time, and another example of the large parts that you can manufacture with this technology. Then the other technology that is becoming more and more popular is binder jetting, and this you utilize a powder that is fused together with a binder. Instead of using a laser, then you use organic material to bind it. Another name for this is 3D printing. This was the original technology. Again, here you need a free-flowing powder, so you can make a bed, a thin layer of the powder, and then you deposit the binder with many nozzles. So this technology is quite fast. You can use it to build individual parts, but why is it becoming more and more popular is because you can have larger batches of this technology. So, and you can work with the powder could be metal or ceramic, glass, sand, or even polymers. So it's very versatile technology. Then the last one is back photopolymerization, which in this case we utilize a photopolymer that reacts with the light. And there are 2 names for it. When you use a laser, it's referred as stereolithography or SLA. And when you use a projector as the light source, you call it digital light processing. This is a schematic of the digital light process. So you have the material, the build platform is on the top, and then the material is deposited on the surface, and the projector is shining the image from below. The materials that you can use is light sensitive polymers that are filled either with ceramics or metals. So this is an example. So you start with a ceramic powder, then you create this paste, and then you process it with this technology to obtain really complicated geometries. And you can do very small details with this technology, such as this screw, or also very larger ones for in this case, medical applications. And just recently, this technology has also been modified so it can also work with metals. So these are the names of the companies that are dealing with this technology, and you can search them if you are interested in this. So, but now all of those technologies that I described in before are a bit more expensive. The machine is very expensive. That's why we started looking into material extrusion for metals and ceramics. So material extrusion is also known now as MEX, and it's a selective extrusion of material through a nozzle. So this material deposition system, you can apply it with a piston, or you can use a screw, or you can use filament. But all of these technologies work in the same principle. So we squeeze out a material through a nozzle, and then we deposit layer by layer in the shape of strands. If we want to make a metal or ceramic part, we have to go through the process which is called shape, debinding, and sintering, or SDS. And here, since we are dealing with the FFF or with extrusion technologies, we tend to use thermoplastic binder and a powder, and then we call this the feedstock, and then we go through the shaping operations. Of course, other extrusion technologies that are relying on pistons might use other types of binder systems, but when we are dealing with screw base or with the filament base, we use a thermoplastic binder system. So the shaping step, it's using commercial equipment, the traditional one that was discussed before, and you have this kind of structure in the material. So you have your particles distributed in the space, and you have the binder system joining them together. And we always try to prevent agglomeration between them. Then you take your shape part and you put it into the debinding process. In this case, I'm showing the solvent debinding process, but there are other methods. And in this case, you remove partially some of the binder, so the light green in this case, which is soluble into this organic solvent, and you retain a bit of polymer left so that the part doesn't collapse when you go to the sintering furnace. So in the sintering step, you fuse together the particles, and you see a lot of shrinkage because of the voids are being closed, and then you can obtain very high densities with this technology. So as I mentioned before, there are different methods of how to do the thermal debinding, and the debinding in general. So the thermal debinding is the simplest equipment. So you just need an oven to do this. And in this case, you have chemical mechanisms that destroy the polymer binder, which are thermal degradation and oxidation. Then you also have physical mechanisms, because the byproducts of these degraded polymers need to diffuse out, and also you have a distribution of the particles when you are doing this debinding. So one of the negative things is that you could have softening of your whole part, and then that leads to deformation and also some stresses. And you need to do this process very slowly. Otherwise, you can get defects like is shown here. So in this case, the sintering was already occurring on the surface, but the polymer was still inside the core of the part, and then you get bubbling effects. And if it's strong enough, the pressure, you can have this little porosity happening on the part. What you can use is TGA to try to see where your binder system it's degrading, and then try to select different steps where you have to hold the temperature and how fast you can go with the heating cycle. Then the next one is solvent debinding, and in this case you use an organic solvent or water to remove the binder system. So this is what I was already describing before. So we have the binder system here, and then we put it in the solvent and we remove partially some of the components of it. Also, again, you have to be careful of how fast you remove the binder, otherwise you can also add some cracks. But after optimization of this, then you can have no cracks during this process. So what happens during solvent debinding is that you have diffusion of the solvent, then the solvent starts to form a gel with the polymer, and then you have this dissolution, so you create a solution. And finally, this solution has to diffuse out of the part to leave the porous structure. So it starts at the surface, and then it progressively continues into the center. and you can recycle the solvents. So you don't need to put new solvents and make it a more environmentally friendly process. What you can do, you can adjust the temperatures, and this is what is shown here, to increase the debinding rate. But again, as I mentioned before, you have to be careful not to do it too fast, otherwise you can have defects in your part. So, and this is an example of a company that is selling materials that are water soluble or organic soluble components. So they are selling ceramic field filaments that you can use for this process. Then the last technology that we have for removing the binder system is catalytic debinding. In this case, the binder system is based on a polyoxymethylene, and you have a backbone to retain the shape during the first stage of the binding process. So the thing with polyoxymethylene is that when you put it in an acidic environment, such as nitric acid atmosphere, then it will sublimate from the polyoxymethylene and will turn into formaldehyde and water and nitrogen dioxide and oxygen. So the sublimation starts at the surface and is quite fast compared to the other the binding technology. So this is an example of the binding process. And in around 150 minutes, you are already in the middle of the part, which is quite fast considering that the other technologies could take the thermal debinding even a few days, and the solvent debinding, of course, hours. So this process leads to the smallest deformation and is the fastest, but you need to get special equipment to handle this. So one of the things is this furnace had to be able to handle a acidic environment, and also you have to have a special exhaust system so you don't release formaldehyde into the air. Nevertheless, this technology, it's being sold as a material by BASF with this brand name Catamol, and the filament is called Ultrafuse. So you can buy these kind of materials already. And then the final step is the sintering step. The sintering step, I'm referring here to solid state sintering. So you have 70 and 90% of the melting temperature in your furnace, and you go from the individual particles all the way. You have some special rearrangements, geometrical rearrangements, so they get closer together as the heat increases, and then you start having neck formations here, and the particles get together, and eventually in the last stages of the sintering process, you get densification of the parts. Another way to solidify these kind of parts is to use additives that could actually melt or just speed up the sintering process. So that's one example here. Then I would like to talk about the strengths and the limitations of the material extrusion process. In this case, the first one that comes to mind is the cost of the equipment. So if you use a machine like this, you have a low investment to begin with. So the material extrusion nowadays, they cost around the hundreds, 300 euros is, for example, this one that I'm showing here. And the very sophisticated ones are 100,000 euros, and it's usually bigger and more precise, right? On the other hand, you have the selective laser sintering, which you have, or selective laser melting. You start with the 5,000 euros, but this is the ones that can work with polymers. And then if you want to actually build metal parts, then you go in the 1 million euro range. So you see there is at least one order of difference between the price of the MEX and the selective laser melting, for example. And you will say, okay, but you need the post-processing. But nowadays in the market, there are companies like NanoE, which are offering the whole package for 10,000 euros, or Desktop Metal, which is a bit more sophisticated and better looking, for 120,000 euros. So it's still cheaper than buying a SLM machine. So that's the first advantage. The other advantage is that you can use different materials. You can have a wide range of powder geometries, because in MEX, When the particles flow, it's because of the polymer is flowing. In powder bed processes, you have to have particles that flow by themselves. So that's a limitation. So you have to have certain size and a certain geometry for powder bed processes. But for mix, you can have all kinds of shapes, like is shown in these SAM images, and they can also have all kinds of chemistry on them. So for some processes like photopolymers, when you add certain metals to the traditional photopolymer resins, they start to catalyze, and then you could have some problems. So you have to have a special photopolymer so if you want to work with metals. And that's why it took a while for bad photopolymerization to start building metal parts. So what we also found out is that if we use the same binder, we can use it with a whole lot of different materials and with standard powders or with experimental powders. So we started our research working with steels, 316L and 74pH. All of these powders are commercially available for many powder metallurgy processes. Then we move our research into magnets, and we try neodymium iron ore obtained from recycled processes, and also titanium, grade 5. And then we started working with ceramics, which alumina and zirconia are examples of them, copper, and the last thing that we did was hard metals and ceramics. Lately, we are collaborating with many research institutes, and we are finding that it's also applicable to tool steels and superalloys. So it's not a problem to use the powders available. The other advantage is that you can use the same feedstock in different processes. So you can start your testing or validating your concept with an FFF printer, and if you see that this is a good part, then the same feedstock could be used with powder injection molding. So that way you can scale up your process. So we are also trying different technologies such as extrusion, and the same binder and the same powder content can be used for all of these technologies. So that's one another advantage. Now I move into the disadvantages, and one of the disadvantages is that you will always get some porosity after sintering. So this is a study done by AM Power, which is a consulting company in Germany, and they are comparing binder jetting, the metal FDM that they call it, the material extrusion process, the laser-based powder bed fusion, and MIM parts. So we can see that the metal FDM has the lowest porosity, so the highest porosity. So they did a direct comparison on the parts, and has some roughness also, and these other big pores, that's a problem. We can try to use other post-processing methods like HIPS to reduce this porosity, and that seems to be working. But this is kind of like a general recommendations for all additive manufacturing process. Then you have also the added porosity due to the printing process. So you have alignment in the areas of movement where the pores are being all aligned. So when we 3D print with a material extrusion technology, we tend to make a perimeter, and then we do the fills in this direction. So you see in these corners, you are developing the pores because material is not covering all the or it's not overlapping the perimeter very well, and this is one process, one disadvantage of using this, and these pores are aligned all over in the same direction, so you have to make sure that you're in the right settings, try to avoid this. And the other thing is that the porosity is also depending on the geometry that you're using. For example, we have these cubes that are cutting tools with hard metals, and we see that it was not really possible to try to get rid of this porosity here due to the infill that we selected and the path that we had in the printer. But when we use these catalyzer supports, the structure is basically just printing perimeters, and we were able to print denser parts with low porosity. So again, the printing strategy is very crucial to try to minimize the the porosity of your parts. Then another disadvantage of using MEX is that you have the highest roughness. So this is a comparison between binder jetting, the MEX, powder bed fusion with laser, and MIM. And we see here in the middle that the metal FDM has the highest roughness in all the directions. So this is Z direction, the mean, and the XY direction. So the best quality is obtained with the MIM, but then you need a mold. So it's not really a comparison to any additive manufacturing method. Then this roughness can lead to premature failure. So because what happens, the roughness acts as a stress concentration points. You have a printed part like this, and then when you sinter, the roughness will remain, it will use a shrink. And this roughness can act as a concentration, stress concentration point, and the failure will occur there. So this is an example of a part tested with in tensile, and we only have a breaking strain of 1.23%, while the rest of parts that didn't have defects on the surface were a bit higher strains of break, around 12 or 10 times lower. So this had to be careful of how you design your parts and how you print them. One of the good things is that you can make a reduction of the roughness by doing what they call green part polishing. So after you shape the part, then you can remove some of the roughness with different technologies, and there is less energy if you do it in the green part than if you do it in the sinter part. So some of our colleagues did some of this investigation. So this is the original roughness of the print part. Then they did polishing with sandpaper, and they managed to get off the biggest defect. But what also happened is that some of the defects of the porosity on the surface become bigger. And the same thing was observed with the sandblasting. So basically the best technology that gave a homogeneous surface and didn't create any further defects is laser polishing, because you locally melt the surface and then you take the material from with excessive into the materials where there was none. So this is the best way to actually treat the parts, which is actually not the cheapest, but depends on what you want your parts for. And then the other disadvantage is that you're limited on the size of the details that you can print. It was already mentioned in the previous presentation. So diameter can be between 0.1 and 1 millimeter. So, and the minimum layer thickness is 0.1. So, and it's also very crude compared to the old technologies such as back photopolymerization. But that doesn't mean that these parts cannot have an application. So I will show you at the end what do we use these parts for. Then when we compare MEX with other processes in terms of the parts complexity, we see here in the x-axis the complexity low and high in this end, and here in the vertical axis you have the number of parts. So this metal FDM or MEX, it's applicable for parts that have low complexity, and you are not going to make a lot of them. So 100, this is what they recommend. So if you want to make more parts with more complexity, then biojetting is best. If you want to make parts that are very simple and lots of them, then other powder metallurgic processes such as press sinter are better. And if you want to have very complex geometries and a lot of them, then maybe MIM is a better way to go. So now we talk about MEX and the processes in terms of the part size and the performance. We see here again that metal FDM it's applicable for low sizes, small parts, and also not a lot of them, right? And similar in terms of the material performance, you go from the average to the good. So if you are in the bigger numbers and better part size or any of these, there are other manufacturing methods that are better suited for that. So Now I will talk about the development of materials for mechs. As you can imagine, this is not so easy, but it's, we have some experience on this, and I will show you what we do. So the first thing that you have to do is to select the powder that you want to use. And if you want to use mechs as your shaping technology, you have to select powders that are similar to PIM or injection molding. You can use metallic or ceramics, and the sizes are with a D19 that will be below 45 degrees, and optimal is around 22 micrometers. So generally, the powders that they are not suitable for powder-based additive manufacturing technologies, you could use in this technology. You can also use smaller particles because they are better for the shape retention, but you have to be aware that below 1 micron, then you can have agglomerates happening, and this could cause some issues during the binding and sintering. So also the shape is quite important. Okay, you can put it anything that you want in the binder system, but if you have very rough particles, then you are able only to put a lower amount of material. And similarly, if you have different shapes, you increase the viscosity of your binder system very rapidly, and depending on the shape, you can have a maximum packing fraction depending on the shape. So ellipsoids, for example, is around 30, but if you use spheres, then you have 40. So also spheres, you can also have a higher fractional density. So it's better if you want to put a lot of powder in your system to use spheres, but it's not necessary. So the other requirements are happening during the printing. So we want to have a filament, in this case, that is flexible and it has strength. So this is, for example, one of the first filaments we made. And if we bend it more than this, then it was breaking. So in order for the process to be stable, then you have to do it with the material basically manually. So this is not very efficient, and it's not a way to build parts. So we had to redesign our material so we can have something like this. The other thing you have to consider is that inside the filament, you have to have good homogeneity. So that means that the particles should be distributed evenly in the binder system. And you also have to have good bonding with the binder. So because that will influence the mechanical properties of your filament. So in this area here, you have to have stiffness because your material is being pushed here and there is a pressure against it. So if it's not stiff enough, then it will buckle and it will stop the extrusion process. It's better if you have low viscosity because then you don't need to use much force to push the material in here. And you have to have good bonding between the layers and not so high shrinkage to prevent deformations and warpage. And also you have to have good adhesion to the printing bed during the printing process, but when it cools down, it should be easy to be removed in order to don't damage your part when you're printing. There's a lot of requirements that you need to consider when designing materials for me. So one of the key factors is to go for a low viscosity. It's a key factor for the production of components with small features. And the way many people are dealing with it is they try different powder contents. For example, here they put 10 volume % of alumina, and here they have 60 volume %. The problem is when you are dealing with the fillers, as soon as you get into the range that we want to have between 45 and 60 volume %, you can be into the parts, the viscosity starts to rise. And if you have higher viscosity, the nozzles that you can use to process the different features are different. So when we have 50 volume % in this case, we were able to use the nozzle of 150 microns. But when 60 volume % was used, only the nozzle with 400 microns could be used. And then the type of features that you can build are higher, right? Also, when you have a higher powder content, then you have more viscosity, and then you have to push harder on the filament. And if it's too high the viscosity, you start grinding on the filament, and then the material eventually stops coming out of the nose. So how can we select the components of our binders? We come up with this flow diagram, and we want to select different components in the binder system. So we want one material that allows to have a flexible filament, another one that adds stiffness to it, and one or two or several additives that will allow to have a good dispersion of the particles inside the binder system. So we make a compound with all of these materials and the powder. So we have the feedstock, then we make filament out of it, and then the first test that we do is to check if it's flexible and it has low viscosity. If these requirements are not met, then we have to start again and select different materials. If this is the case, that we are a flexible material and we have low viscosity, then we try to put it in the solvent to check the binding process. We check then if after being in the solvent you have any defects. If yes, then you have to think again what kind of additives or what kind of polymers you want to use. If no, then we go and check if the material is printable at a reasonable speed and without a person feeding the materials. If this is not the case, then we have to rethink our formulation at the beginning. And if this is the case, then we have our recipe that we can use. So now I'm just going to give you an example of how we to optimize a formulation that we develop. So we started with a flexible material, which is the SABS, and then a rigid material, which is this HDPE grafted with acrylic acid, and an additive, which is stearic acid, which is used to disperse the particles in the binder system. And we fix the amount of zirconia powder that we use. What we saw is that it was flexible, but it has a high viscosity. So the viscosity has to be low in order for us to be able to print smaller features, like I mentioned before. So what we did, we replaced some of the SABS for paraffin wax or extended oil, and the rest remained the same. And what we observe is that we have changes in the flexibility when we have these additives. The green curve here is the SABS with zirconia, but no other additive. And we have the highest strength, right? This is the strain and the stress. Then when we add the paraffin wax, we have a decrease on the strength. It's not so bad compared to the extended oil. So we already started thinking that the paraffin wax, it's a better additive than the extended oil. Then we went into comparing the viscosity. So first we tried this on the on-field binder systems, and in the first case we have the SABS with no additives, and we can see that the viscosity is quite high. And then when we added the paraffin wax and the extended oil, we decreased almost 2 orders of magnitude on the viscosity, which is quite good. So we can conclude that the paraffin wax and the extended oil can be used to reduce the viscosity. And this was also observed in the feedstocks, not just in the binder. So, but the level of reduction between paraffin wax and extended oil was the same. So still more points for the paraffin. Shape the part. This is the case when the SABS was used. And after being in cyclohexane for 6 hours, we obtained this kind of results. So we have very big cracks on the surface, and that means that this is not a good way this is not a good binder system. And the reason for that is because we had these very big structures in the binder system that when they are removed, they lead to cracks in the surface. So similar results were obtained with the extended oil. So these big structures still form, and then that led to cracks on the macro scale. only paraffin wax was the better one that didn't give any of these large structures in the green part, so that we have less cracks in the components. So these platelets are the soluble components. So now, just to conclude, I want to give you some applications of the MEX process. What kind of applications we can expect for these kind of parts. And first, we have already many different companies that are involved in this technology, either supplying equipment such as IAM and Poland, which they want to use MIM feedstocks, so their systems are based on a screw-based extruder. And then you have other equipment and material suppliers such as Desktop Metal, Appium, Evotech, Markforged, and other material suppliers like BASF and Nanoe. So this is gaining some popularity because it's an easy technology, so a lot of people are now getting more and more interested in this kind of materials. One of the applications that we find for ceramics, for example, was to create supports for plasma catalyzers in the case for air purification. So this is the reactor that we use. So we have an inner electrode here and an outer electrode, and between we have high voltage on it. And in this area, we have the place where the reaction occurs. So we put the pollutant in the top, and then we have the byproducts after they go through this high voltage field. What we did, we prepared two different geometries, one with axial channels only, and one with axial and radial channels. So this geometry with axial channels could also be done by extrusion, normal profile extrusion. But this one with the axial and radial channels, that would be almost impossible to do. So that's the advantage of additive manufacturing. Then what we observe is that there is less energy with the bidirectional channels. And this is the power consumption for the gradient toluene when we use just the plasma. So that means no support structure and no catalyzer. We consume around 9 watts. When we put just the axial channels, that we actually increase the consumption because there was an increase on the resistance, right? So the electrons had a hard time getting to the reactant, so you need to use more power. But when you have the axial and the radial, we went below the just plasma. So that shows the advantages of using a bidirectional catalyzer or support structure. Then another advantage is that we can create multi-material parts. It's not so complicated to do this once you design the correct feedstocks. You just have to have a printer with 2 different nozzles, and then you can print a part here. In this case, it was steel, and the outer part was zirconia. And then after sintering, we see that the shape is retained, and there was no delamination between the different materials. This was just cut off so we can see the inner structure of the steel. So, and we prepared 8 different heaters, infrared heaters, and then we tested them. So what we observed is that it's more or less repeatable, that we can put a certain amount of power into it and reach a high temperature. So these structures are actually functional, and they can be manufactured very easily with MEX. So other applications that are more structural are actually for tooling, and this is the work done by Markforged, and they're showing here this housing that instead of machining it or casting it, you can build it with a 3D printer from Markforged that works in the same principle I just explained. And this could be used for spare parts, for example. Other examples that they give are crucible clips here, these ones here, and also lifting tools. So this technology is of course suited for very low volumes of production and very large to medium parts. So spare parts could be one of them, or one-of-a-kind lifting tool. It's okay for this technology. So just to conclude, I have shown that MEX can be used for metals and ceramics. Once you develop a special feedstock that needs to fulfill a lot of requirements, you need to have a multi-component binders in order to meet all of these requirements that are needed during shaping, during the binding, and during sintering. And MEX can be used as a current technology to produce certain parts for special applications in low volumes. So that's the end of my presentation. So if you have further questions, please ask them now or send me an email to this address.
Thank you, Amin, for your interesting presentation. And we already have 2 questions. The first one is, do you have a specialized nozzle for material extrusion? And can you give some details about it, if this is a special nozzle?
Actually, no. You can use whatever nozzles you use for producing plastic parts, but it depends on the printer that you have. You know, what is important when you're dealing with these highly filled materials is that you have a compact printing head with a short nozzle. So, but there are printers for plastic that have already this configuration. So it's better to have a short nozzle than a super long one. So that would be the only recommendation I will give. Other than that, the geometry, inner geometry of the nozzle is the same, like for plastics.
Okay, probably you can expect more wearing in case of this highly filled.
Yes, especially if you are dealing with ceramics, which are very abrasive, and your nozzle is made out of glass, you can see how the nozzle diameter increases as the number of parts are printed. So hardened material will be useful. Yeah, that's another recommendation. Yes.
Okay, and another question is, how do you measure the viscosity of the material?
Well, there are different ways. So the more practical way is you can do capillary rheometry, but this is time consuming and expensive. But this is the most appropriate way to do it. Because you want to be in that range of shear rates where the extrusion process is happening. So capillary rheometer would be the best, but if not, then you can just have MF5 as a value and then compare it to traditional to different materials. So it would be more like a comparative effort rather than an actual measurement of the viscosity. But those 2 things can help you determine if it's too viscous or low viscosity.
That was the topic described last week on our workshop when your colleague Ivica Juretek has a quite interesting presentation. So if someone from audience would be interested to get those materials, you can send me email and I can send you back the presentations. This methods of determination of the properties of the material for the material extrusion technologies are in detail described in last week when we had a workshop on also under our project. So Yamin, thank you very much. We are 5 minutes or 4 minutes late with the break, and I hope that we can start after the break at 13:00 according to our time, or 12 according to Greenwich Mean Time. So thank you very much for all presenters. Thank you very much for all participants, for questions, for the answers, and we will proceed in within the next 25 minutes or exactly at 13:00 or 12 at the Greenwich time. See you. Bye. Area, so there are a lot of work and efforts on creating standardization for additive manufacturing processes and technologies. And the second presentation will be about functional graded additive manufacturing. So I think that Dr. Pei will be the first presenter of those two lectures. So Eugene, please.
Thank you, Dharma. Well, I'm just going to share my screen and then I'll get started with the presentation. So I'm just going to switch over to my PowerPoint slides. I'm just going to share that now. And I'm going to switch that to full screen. Okay, I believe you should be able to see my screen. Can you confirm that, Dharma?
Yeah, we can see it. We can see it.
Okay, that's great. And you can see me as well. Fantastic. Okay, shall we get started? Okay, well, let's start. So I just hope that you guys have had a good lunch. Although it's such a short break, but we just wanted to make you obviously aware about technology improvements and progress in additive manufacturing. So what I have here with us for our first part of the presentation from Brunel is about standards. And I think standards are going to be increasingly important as additive manufacturing becomes more mainstream. So this presentation hopefully will provide greater awareness, and you'll probably be able to understand where we are in terms of the state of art of standards, important projects, documents, standards with regards to what different groups are working on at the moment, different drawing groups, different working groups, both from ISO and ASTM. So hopefully we'll get an understanding of standards, and also to try and show in particular within the field of data and design for additive manufacturing as just one example within the field of standards. So I just hope that you enjoy this presentation for today. Okay, so just to get us started, I'd like to explain to you or share with you more about my background as well as my co-presenter's background. So for me, I work full-time within Brunel University. We're based in London in the UK. And my full-time job is Director of Postgraduate Research as well as Director for Product Design Engineering, looking into the PhD programs as well as for the undergraduate programs within the Department of Design in the department. And in terms of research, I've got research focus on design for additive manufacturing, or what we call DFAM, and also on 4D printing, which is about the use of shape memory materials for metal extrusion in 4D printing, looking into applications into novel emerging technologies. So that's, again, the two aspects of my research focus at the moment. In terms of standardization, I'm involved at an international level. So I chair a working group mainly for data and design within ISO Technical Committee 261 and within Working Group 4. We'll go through more about what those working groups do in ISO level. Then we get a better understanding of where data and design fits in. And my co-presenter, Dr. Iswa Keba, she's with us today. She works closely with me as a research associate in additive manufacturing, also in Brunel University. So she's got expertise not just in additive manufacturing, but in particular for functionally graded materials. And she's got a presentation after me to explain what functionally graded additive manufacturing means and what sort of materials are. Also in terms of FEA, or finite element modeling, advanced laser surface modification treatment of metals and alloys, as well as in metallography. So she's an expert in those areas. And together we work as part of the Annex Adam project in terms of standards in FGAM. So in terms of this slide, what I'd like to do is to obviously introduce the key topics for the presentation on additive manufacturing standards for data and design. But first of all, we need to understand the concept of standards. What are standards? What are they and why they're so important to us? and then later to go into detail about the American ASTM F42 committee, which looks into additive manufacturing within ASTM International, and follow that with ISO TC261 working group and drawing groups. And further down, we give you an example about data and design standards related to the entire EM process chain. And because of time limitations, I'll only be able to show just one example of a published design standard. We will go into detail about the powder-bed fusion of metals as one example, and then to also share with you some useful external resources. So collectively, I hope that this presentation will be helpful just to generate better awareness about the importance of additive manufacturing standards and work relevant to your job scope. So I've got a question for all of you. Obviously, with lunch, you might be feeling a little bit sleepy. So really want to make sure that all of us are, again, interacting with each other. So I've got a question. So here, the question is, tell me, what are standards? Maybe tell me mentally. Okay, hopefully I can be able to tap into your hypnotic brain, and then hopefully I can get into what you're thinking about. But mentally, tell us, what are standards? You don't have to type or say anything, but are standards a technical document used as a guide, a guideline, or a rule or definition? Is it a technical document which is a rule or a guideline definition? Or B is a distillation, a distilled condensed wisdom of people, meaning the knowledge of people with that particular expertise in the subject matter. It's not about what form it takes, it's not about documents or software, but it's a distilled wisdom. Okay, so is that a standard? C, is it a document that describes the correct way, an agreed way of doing something, how to do it, and what should be done? Is that what standards are in a form of document? D, is that going to be like a common language that we speak in order to tell us how to measure and determine or evaluate or verify the performance of something? Or E, all of the above? Okay, so standards actually can come in different sorts depending on your own interpretation. And the answer actually is E. It's all of the above. So sometimes standards may not really necessarily be in the form of a hard, thick document, but it's actually in the form of maybe a guideline or maybe in the form of a report. But effectively, it's a rule, it's a definition, it's an agreed way of doing something, but specialists in that subject matter, maybe also to measure or evaluate the performance. Okay, so let me give you an example. I'm sure you have seen the picture on the left, which is a very interesting representation of an elephant. Okay, and on the right, we'll talk about it later. But on the left-hand side, there is a story about the 6 blind men and an elephant. I think the blind men are a little bit invisible. We can't see them clearly, but it's actually yellow spotted images next to the elephant. But what it's trying to tell us is about the 6 blind men and an elephant, meaning that if you are, well, for example, visually impaired, you cannot see. And if I were to ask you, how does an elephant feel like or look like? And if you cannot see, you'll be touching and feeling a real elephant at different locations. Maybe if you feel the tusk would look like a long trunk, which is actually maybe a different object. Maybe it's not a trunk, but to you might describe it like a sphere, okay, a spear. Or if you touch the belly, it looks really rough. It looks like a brick wall. If you touch the legs of the elephant, it looks like a tree trunk, very, very rounded, hard. So if we don't have standards, it means that 7 things, the way we do things, it's open to interpretation, and there is not going to be a kind of commonality to it. And that causes a lot of problems when it comes to trade in the industry or even for manufacturing. So with standards, looking at elephants, when it comes to standards, we know that in the scientific way, elephants can be classified according to 2 taxons or two classifications, African elephants and Asian elephants, and there are very specific requirements or parameters. An African elephant has large ears, whereas an Asian elephant has smaller, more rounded ears. You can see in the picture in there. So it tells you a very defined classification of what to look for when it comes to elephants without having to interpret it in the way we like it. No, it's being defined already. So the whole thing about standards in principle is actually a published document that describes either a technical specification or a list of guidelines, which will be able to help us to understand which are the rules or definitions, even the methods or the way we need to use certain words in vocabularies or even codes of practice, best practices in doing something, so that it's a unified source of reference. It's one common, either global or regional reference in order to specify or represent products, services, or manufacturing activities. That's the key about standards. It's a standard guide. And in order to implement that, we need to have an organization. The organization is a recognized way to develop and implement the standards as well as the certification process. So these organizations principally act in the form of 3 different levels. First, at the national level in our own country. Second, standardization bodies work at a regional level, for example, within Europe. And finally, at an international top level as a complete joint system. So let's look into the 3 levels. For example, as mentioned to you, at the national level, you have your own national standardization body. For example, in Croatia, the HZN or Croatian Standards Institute would be the representative at the national level for companies, local organizations, local universities and institutions. If they got an issue or a question or even a proposal, then the HZN or Croatian Standards Institute will be the first point of contact at the national level. And collectively, all of those national standardization bodies, whether the British Standardization Organization, the HZN, or whatever it is at the national level, then they work together within the region to make sure that there are compatibility standards and there are also no conflicts. There are also no issues between standards that need to be uniform. That's why we have regional standards, because some products or services need to serve or need to be delivered at a regional level. Maybe you want to have a product which is going to be sold just within Europe. Then for additive manufacturing, SAN TC 438 would be the responsibility for additive manufacturing standards in the European Union or within Europe. So SAN TC 438 would be key if you wish to take this further beyond the national level. And there are different regions, obviously, looking at different standards. For example, SAN looks into the European Committee of Standardization, but then you have SENELEC, which is about electrotechnical standards, maybe for 4G data, for example, for 5G. Then you also have telecommunications for ETSI, which also looks at similar aspects of electrotechnical mechanisms for services. So you need to know at which level you need to go to. And finally, obviously, at the national level, we have the ISO or International Standardization Organization, and similarly for SENELEC and ETSI, they have the IEC and ITU. So this would be how we see standards coming from a document, looking at the document at the national level, followed by homogenized documents at the regional level, and finally uniform documents at the international level. Okay, so in some instances, that document might have been adopted at both national and European level. That's why within the UK, we see BS/EN ISO something, meaning that it has been adopted at 3 levels. Okay, so think about standards at the different levels. Now, obviously, for additive manufacturing, we want to look into a top level. In principle, ASTM F42 and ISO TC 261. We need to understand what is the relationship between both organizations and what do they do. So for ASTM International, the F42 committee looks into aspects of additive manufacturing standards just in North America. Okay, so that's for the F42 committee. Whereas for ISO, it's an international standardization organization. It doesn't include America, unfortunately, but it's collectively as an international organization that represents additive manufacturing within technical committee to TC 261. So ASTM F42, initially before 2011, they were coming up with standards for additive manufacturing. And at the same time, ISO was also coming up with their own standards for additive manufacturing, and it became a little bit confusing. So in order to avoid confusion, in order to have a much more coordinated approach, both organizations decided to sign a PSDO cooperation agreement. PSDO referring to Partner Standards Developing Organization Agreement, so that any standards coming from America for additive manufacturing or any standards coming globally from ISO would match each other, would be homogenized. So which is why you will see for additive manufacturing standards, it will be ISO/ASTM followed by the code of the standard. It's unified, meaning one standard for the whole world that avoids confusion. Okay, so within ASTM F42 and within ISO TC 261, there are a number of standards that have already been published and also a number of standards that are still in development. So within TC 261, we know in the website, it shows that they have at the moment 18 ISO standards related to additive manufacturing, and it's growing every day, every week, every month, every year. You'll find new standards being developed and being published. Typically, it takes about 36 months, sometimes 40 months for a standard to be developed. So it's a very, very long process of review, scrutiny, and approval at different levels, at the national level, regional level, and international level. So you can be assured that every standard that you either get access or you read or you purchase has gone through a very thorough process of scrutiny to make sure that you get the information correct, and it has been checked at many stage gate approaches. At the moment, we have 25 participating country members and 8 observing country members as part of this organization. And you can see also in the center bar of this slide, some of those published ISO standards. Just an example would be, some of them would be the old ones, ISO 17296-2, which was published in 2015, ISO 17296-3, which was published in 2014, and ISO 17296-4, which was published in 2014. Those on the left-hand side are now in the progress of revision, because those standards on the left-hand side are more than 4 years old. Every standard document is typically revised once every 4 years. So I can tell that in my committee at the moment we're revising 17296-4, which will then be made known as ISO ASTM 52950 2020 or 2021, depending on when it's going to be published. So that's the scheme of things. And on the right-hand side, those that have already been jointly published by ISO ASTM quite recently in 2018, 2019, 2020, include more specific standard documents, like for feedstock materials. What are the methods to characterize metallic powders, maybe for powder bed fusion? What methods to use? Then that document 52907, which has been endorsed by ISO and ASTM, would be the guide for you to look into the methods to do characterization of metal powders. Similarly, for 52910 about design requirements and guidelines, or as well as 52911-1, which we will go through a little bit into detail about how to design parts for laser-based powder bed fusion, specifically for metals, because 52911-1 is for metals, 52911-2 it's for polymers, although it's from the same powder bed fusion process. Okay, so this is just an overview about what ISO and ASTM have been doing, and to also explain to you the standards that have been published and what are those that are under development. If you go to the website, if you click on 18, it tells you the list of 18 published standards. If you click on 29, it tells you the list of 29 standards under development. Then you can find out more about those standards if you are interested to learn more. So again, just to share with you a little bit more about ISO, about the ASTM F42 subcommittees, because F42 is such a big technical committee, they have smaller groups or what we call subcommittees. Each subcommittee is responsible for a particular scope, particular area of expertise or specialization. So we can see, for example, in F4201, it will be all about the testing methods related to additive manufacturing. So regardless of what kind of testing methods, that tensile test methods, but whatsoever it is, if you're interested to know more about how those standards are being published or you want to be involved, then F4201 committee would be the guys there, the experts there looking into test methods for additive manufacturing. So earlier this year in 2020, the ASTM F42 created a series of subcommittees specifically for applications. That was F4207, as you can see in a blue colored table or blue colored cells in this table. So in the blue colored cells, you can see that within the applications F4207, they have broken it down into 9 subdivisions of specific applications for additive manufacturing. Aviation, space flight, medical applications, heavy machinery, maritime or shipbuilding applications, electronics for additive manufacturing, construction, oil and gas, and consumer. Obviously, there is a danger of some subcommittees might have a little bit of overlap or what we call scope creep, because aviation and space flight have some relationship with each other. So there might be some overlaps across some of those. So in order to prevent that, the parent subcommittee F4207 will make sure that those later what we call children or associated lower rank of the committees make sure that they tie up properly in terms of their activities. And also within ISO, or ISO International Standardization Organization, TC261, we have our own working groups. It's a little bit more simplified in the sense that we don't have a working group for application, but we have working groups in what we call a working group for the terms and vocabularies, just for the terminology, because we want to make sure that at the international perspective, when somebody says the technology is for powder bed fusion, what is powder bed fusion? Should it be bed fusion for powders, or should we call it powder bed fusion? So that working group 1 looks into the vocabularies and terms used for additive manufacturing, which has a lot of implication in terms of education, or even if you want to sell a product, you need to know what is the right name to use. Working group 2 looks into technology, mainly in the process and from a system approach, as well as specific aspects of material. Working group 3 look into test methods and quality specification. So you can probably know that for working group 3 test methods, we'll work very closely with ASTM F4201 for test methods. So there's a relationship between subcommittees for ASTM and also for ISO, and make sure that there is some common understanding and good working relationship. And obviously there's working group 4 for data and design, which we'll touch into that later. Then working group 6, which looks into environmental health and safety. Just remember, there is no working group 5. For some unique reason, there is no working group 5 within ISO TC261. Then there is no working group 7. Followed by that, working group 6, we jump to what we call a joint working group. There are at the moment 3 joint working groups: joint working group 10, 11, and joint working group 1. So the numbers are jumbled up. Joint working group 1 is a joint working group with an external technical committee, which is ISO TC44, that looks into aspects of welding. So ISO TC44 works with ISO TC261 to come together to form ISO TC261/ joint working group 10 that looks into aerospace. Okay, so this is for aerospace area. And then finally, joint working group 11 looks into aspects of plastics together with ISO TC261/ SC9 for polymers. And then there's one more which has been recently formed, which is ISO TC150 in terms of surgical implant applications with joint working group 1. Okay, so these are this is the setup for the working groups within TC261. Okay, so now let me go through a little bit into detail about the scope of TC261 working group 4, because this is a working group that I'm very familiar with. And what we do within this scope is that we try to work together to standardize aspects of data and design related to additive manufacturing. including but not limited to data processing. So how we actually exchange data in terms of the right type of files, file formats, the metadata involved. Maybe we mentioned about STL, 3MF, AMF. We talk a little bit about the specifications. We talk about data security. So that's about the data. And then also within this working group, we look into general and specific design guidelines. General meaning it's not machine specific. General meaning a top level guideline for somebody who wishes to adopt additive manufacturing, and also process specific design guidelines. So you have a design guideline, say for metal extrusion, design guideline for powder bed fusion, design guideline for electron beam melting. We do have specific design guidelines for those processes because each process has a very different mechanism, and we need to take advantage of those mechanisms so that we can be more effective and more efficient in the way we want to do things. So within Working Group 4, as mentioned before, we have different joint groups. In total, we have 7 joint groups that report to the parent committee of Working Group 4. So in Working Group 4, you have Joint Group 54, which looks into design decision guide. Right, documents related to design decisions will be developed by Joint Group 54. Joint Group 55, they look into metal extrusion, which is quite unique because it reports to Working Group 2. Because Working Group 2, they look into materials and systems. It's quite unique kind of agreement. Then we have Joint Group 57, which looks into powder bed fusion. Joint Group 64, that looks into data transfer formats and the AMF file format. Joint Group 67, which looks into functionally graded additive manufacturing or multi-material manufacturing. Joint Group 70, which looks into medical imaging data that comes from CT scan, CAT scan data. How do you convert CAT scan data to make sure that you can get those point clouds attributed and getting it sliced for manufacturing? Joint Group 73, which looks into data packets as well as data management for additive manufacturing. So Joint Group 73 and Joint Group 64 again have a relationship about data, and the rest would be much more towards either design or image optimization, because we are all together about looking into aspects of data in design for additive manufacturing. And collectively, we meet either face-to-face if possible. If not, you will be through emails, Skype, or other forms of dialogue. So if you're interested, contact us and we can direct you to the right joint group or the right people involved, depending on your area of inquiry or the area of expertise that you need. So as you can see in this slide, you have the working group 4. Within each working group, an example is a joint working group 54. And within joint group 54, which looks into design decision, they have what we call a work program or projects. And each project will then have their own project members. Typically, project members from ISO and members from ESTM, usually between 10 to 30 members within that specific work program. So 52910, you'll probably have a few people working together to come up with guidelines for requirements and recommendations when you want to use additive manufacturing. And similarly, for PWI 52923, PWI refers to a preliminary work item. They look into aspects of design decision support. So collectively, we have all of those joint groups, and each joint groups will have their own work programs or their own projects. And you can see different projects are clustered differently. So for example, joint group 54 is about design. Joint group 55, which is quite unique, is about metal extrusion. Joint group 57, which is quite a busy active joint group. Joint group 57 has got 4 projects at the moment. 57 looks into design guideline for powder bed fusion, which part 1, we'll go through that later. Part 1 is about laser-based powder bed fusion of metals. Part 2, laser-based powder bed fusion of polymers. And part 3, which is about electron beam melting with powder bed fusion of metals. And finally, in joint group 57, they're also looking into DED, or directed energy deposition methods. But it's again design guidelines for DED. Okay, so this is what's happening out there. But I can tell you that there are also a lot of other background activities. For example, in joint group 57 is also looking into material jetting, which is not here. But material jetting is really an active group looking to come up with a PWI, which is a preliminary work item coming up soon. So hopefully within joint group 57, we will have a list of process-specific design guidelines. In the next page, we have drawing up 64, which looks into data, in particular the AMF file format. At the moment, we're looking into version 1.3 for the additive manufacturing file format, which is the only recognized file format at ISO to support additive manufacturing, because it's backward compatible. It's also not machine specific. You can include metadata. You can do constellations meaning the arrangement of parts, so that when you save the AMF file format, how you want to arrange the parts is already predetermined. You don't need an external third-party software to do that. You can do nesting. You can include textures, materials, even colors in the AMF file format. You can also include units, for example, millimeters or SI units, which maybe the STL file doesn't offer you. So the AMF file format, it's very, very powerful. And in version 1.3, we also include aspects of data encryption for security, as well as a little bit into what we call metadata for data logging within version 1.3. Now, drawing up 67 looks into two projects, which is 52912 on FGM, and as I mentioned to you, 52950, because 52950 used to be called 17296-4, which has been renamed to 52950, regarding an overview of data processing. Drawing up 73 looks into optimization of medical image data. That's where the medical people are. Maybe you've got a CT scan of your arm, of your bone, and then they tell you the processes you need in order to optimize the image for additive manufacturing, because you have to do some error correction, compensation. You also need to make sure about patient confidentiality and things like that. And finally, in drawing up 73, they look into data packages for additive manufacturing parts. What kind of data should you include inside additive manufacturing parts? So as we move on to the next half of this session, I'd like to share with you just one example about a process-specific design guide. And here I think I've chosen one example, which is an ISO ASTM 52911-1 version. It's the first version which was published last year in 2019. It took us about 2.5 years to get this approved, to get this endorsed by both ISO and ASTM. In part 1 here, it tells us an overview about the design guidelines associated with the use of specifically powder bed fusion of metals. And there is also a translation in French, because actually in international standards, which officially translate that in 3 languages, in French, not translate in 3 languages. There are 3 languages available, obviously in English, in French, and also in Russian. These are the 3 main languages available for international standards. So here in 52911, there is also a French version below. I can't speak French, but you can see the text in italics right at the bottom on the lower right corner of the document, which is the front page. Now here inside 52911, I don't want to go through all of those details, but I just want to show you some exciting pictures and some illustrations that I think could be quite helpful to your work. So if you're using additive manufacturing and in particular fusion of metals for the very first time, you want to listen to some advice, or you want to get some inputs about some good industry best practices about the way of doing things when it comes to powder bed fusion of metals. For example, the orientation is going to be very important, because the orientation of parts within that build platform has a relationship with the spreading system, or the wiper, or maybe what we call the spreader, in order to make sure that you distribute the powder evenly. But as you build parts, if your part is very thin walled and your part is very long, and if your part has a lot of contact with the wiper, then that part might be not just hit, but the amount of pressure of powder pushing down, that part might be slightly distorted. There is a risk to do that. So the guidance that in table 3 in the document is to suggest to you some good practices to say that if you're thinking about the orientation, then it should be oriented in the part in which the contact length of the spreading system should be minimized as good practice. Don't adopt the poor practice, because it has been done before, and very often you find that parts will fail, or parts are not built up to certain quality. And obviously on the right hand side, they give you guidance. If you are printing many pieces of multiple parts, the best way is to make sure that you position them such that the contact length of the spraying system can be minimized. Where here in the example on the furthermost right-hand side, the best approach would be to stagger them or to arrange them with a slight offset so that when the spraying system moves, you will minimize the amount of contact for each particular part in that build space. Now, this is a very simple example of some guidelines we provide in a pictorial form inside 52911-1, in particular for metals. And there will be a different guidance for different process, because obviously for metal extrusion, you don't have a spreading system. Then you will tell it for metal extrusion, what are the do's and don'ts for the extruder? What are the do's and don'ts maybe for metal jetting, and so on. Okay, so here in terms of the review of 52911-1, other aspects inside this document, we look into the characteristics of powder bed fusion processes, some key characteristics, what to expect in there, what are the benefits, the cost benefits when you want to use powder bed fusion, so that you can compare this also with other documents that may be mentioned about metal extrusion. You can see the benefits in there, and also what are some of the limitations you need to think about if you want to choose powder bed fusion. The drawbacks or the constraints or the restrictions and limitations are also spelled out inside the document. And then on the right hand side in the document, we also try to demonstrate and to show you what are some of the key feature constraints, in particular for islands or unique parts that stand on its own, or overhang surfaces, overhang features that are more than 45 degrees, what to keep in mind, how to minimize the stair-stepping effect in order to improve the resolution of parts, how to ensure that you get good dimensional form and positional accuracy with respect to thermal influences in powder bed fusion. And also we talk about data quality, resolution, and representation inside 52911-1. So it's a very comprehensive document that has already been published last year. I would really advise you to take that on board if you feel this would be useful in your work. Again, here you can see within the document, in the last pictorial example is about the considerations for design, because this is a design guide. It's not a process guide, it's a design guide. So if you wish to include features like holes, cavities, gaps, or even to make changes in the thickness, or even markings, integrated CE markings or integrated detailed markings, or even channels or lattices, lattice structures, what should you consider? So for example, on figure 8A in the center of the slide, you can see that this was the initial shape. Obviously from the original CAD geometry, from solid modeling, you have already done some intelligent, what we call topological optimization to minimize supports and minimize parts. Then in 8B on the right hand side, they suggest if you are using laser-based methods for powder bed fusion, some key details that could be considered would be the thickness and the length. And also, if you can see in that orange or yellow colored arrow in Y, they suggest that if you wish to do without supports, then the red arrow in Y below suggests that potentially a teardrop shaped profile could be considered, because a teardrop shaped profile will not require you to have any support structures. Importantly, if this is going to be concealed like a pipe, you will need support structures which you cannot remove. Then the document suggests why not a teardrop shape, because anything more than 45 degrees in principle, because of the rules of gravity in physics, you don't need any support structures. This could be a consideration if you choose to use powder bed fusion. They tell you other things. Maybe you need a hole in order to shake off the powder, the unsanded powder needs to be actually released off. They tell other things about post-processing, about support structures and things like that. So this is a very helpful guide supported by illustrations and figures inside. Okay. I think my time's running out. It's already 40 past 12. So I just want to also summarize the work that we do within Working Group 4. Obviously, other working groups, they've got lots of activities within there, but within Working Group 4, we see ourselves within the process chain of design decision support. We have got 2 key documents for you to refer to. In terms of additive manufacturing data, we do have 4 key pieces of documents for you to refer to. And then AM process specific guidelines, as mentioned to you, we have metal extrusion, laser-based powder bed fusion of metals, polymers, and also in terms of energy deposition and electron beam melting. And finally, in terms of AM applications about FGM parts, which you will know a little bit more about FGM from Israt's session just after me. And finally, also on medical image data. So we cover the entire process chain. We know that there are still gaps, and if those gaps can be filled in, tell us. Maybe there was a gap about design for post-processing. Maybe for medical parts, you need more guidance about how do we actually clean those parts. When it comes to the designing stage, maybe there should be rips or there should be more holes, then there should be a new project. So if you wish to be involved in a new project, get in touch with us, get in touch, or maybe it can be from one of your research projects that you know can fit into one of those documents or fit into one of those activities. Then get in touch with us, and we'll be very happy to at least acknowledge your work and use the results from your research projects to fit into what we call a design guideline for additive manufacturing. Okay, so this is going to be one of my last few slides now. This is really, I think, 12:42 or 1:42 if you're in your CE time, Central Europe time. So some useful resources. I thought the first point of this first destination might be the ISO website itself. And this website is specifically for ISO TC261 committee's webpage. It's constantly updated. It's about the news, when is the next meeting, how you wish to be involved, what are some of the new developments of standards, some of the projects we do at the European level with SEN TC438 with different national committees. And then you also have the ASTM F42 subcommittee website in there. Check it out. You could choose to be a member of ASTM F42 or a member of TC261 or either one of the other, depending on your own requirements. Then you also have the Creation Standards Institute's website or HZN. And finally, some of those questions, common questions and answers about ISO, about maybe what is a technical document, what is an NWIP. So those terms or those vocabularies or the glossary, you may not be very sure. And I thought that this website, iso.org/glossary.html, could be helpful just in case you have those questions that might come across when you read the standard. Okay, I think it's really about 12:43, so a little bit faster. I should be finishing about actually 1:45, but just 2 minutes fast. So really appreciate your attention. I hope nobody is sleeping. I hope you guys are still awake and listening to me. So my name is Eugene. Thank you for listening. And my co-presenter Israt is also with us. I'll be happy to take on any questions that you have. So I'll probably stop sharing my screen and I'll switch back to the main window. Any questions, please try to use the chat box. Zama will help us. Thank you.
Thank you, Eugene, for very comprehensive information about what is going on with the standardization in this area, because it's very important from the fact that additive manufacturing is using more and more for very serious applications. And today, without standardization, it's very difficult to assure high quality. And I hope that you will be very successful in your future work in this area. So, so far I cannot find any question for you, but if some questions will arise in the future, we will be in contact, and everyone have my data for contacts, so there will be no problem.
Thank you.
Yeah. Thank you very much for your support again. Bye. Well, the next presentation is from Israt Kabir from the same Brunel University, but she had some experience with low connectivity with the internet, and connection was not so good. I hope that everything is now okay, Israt. And if your connection is now okay, please proceed with your presentation about functionally graded additive manufacturing.
Thank you, Damir. So, okay. So Tomislav can play that things for me. But although my internet connection is stable now, but yeah, I would appreciate Tomislav if he plays that for me. the recorded video, please.
Okay, Tomislav, please, can you put the video?
Unfortunately, I'm having some issues, so just let me solve them.
No worries, I'm here for that. If the sound's quality is not great, then I will switch back to the live presentation. Yeah.
Israt, I think the best is you continue live, because now I don't know why, but I cannot turn it on.
Okay, no worries. Yeah. Okay. So shall I proceed?
Yes, please, Israt, if you can do it live.
So I started sharing. I hope you all can see my screen clearly.
Yeah, the screen is.
Okay. All right. Hi, good afternoon, everyone. So after my colleague's presentation on standards, I would like to, he already introduced me. We work in the same group, and another expertise of our Brunel design team, Dr. Eugene Pei's team, is functionally graded additive manufacturing. And I'm Israt Kabir. I work as a research associate for the Onyx Adam project. And I'm going to talk about mainly the functionally graded additive manufacturing. I will start with the progress of additive manufacturing, which actually leads to the production of this special type of composite material called functionally graded additive manufacturing, with the concept and classification of functionally graded material structure, and the process chain of FGM technique, especially the design and modeling, along with the technologies to manufacture the FGM part, the potential applications in design and engineering, followed by some future directions which can leverage the full potential of functionally graded additive manufacturing. So we all know about additive manufacturing process. Our colleagues already have described a lot, and we all know that there are 7 types of basic additive manufacturing processes declared by ISO ASTM standard. Each process can be derived into different names by just altering process mechanism and some technological alteration. So additive manufacturing offers a lot of advantages over the conventional manufacturing processes in subtractive mechanisms such as CNC. It offers improved design, functionality, and performance of the product, including the design freedom, increased customization, and shorten the processing chain of the manufacturing technique. So understanding the advantages of additive manufacturing allows the designer to make better decision in terms of right choice of technology and to produce the optimum products. It also paves the way of topology optimization technique, which can create the strong light optimized part for the additive technology. over the years, there are huge progress in additive manufacturing is happening very fast. So by reoptimizing the operation of additive technology and redesigning the products, one can actually produce a multi-material part in single manufacturing state through additive manufacturing. And it explores the other type of materials driven by the manufacturability, like glass and ceramics, into different complex forms and shapes. So these technological advances in additive manufacturing process leads to that in creating parts of functionally graded material, leads to the term called functionally graded additive manufacturing, where material characteristics and properties can be varied according to the composition, phases, and microstructure at predetermined location in a 3D objects through voxel modeling. So functionally graded additive manufacturing is basically defined as a layer by layer fabrication process, which involves the material gradation and compositional variation within a component to achieve some intended functions together. So comparing to the conventional multi-material composites, FGM blends multiple materials gradually rather than sharply, rather than having a sharp change at the interface of each material, which creates the continuous changes in the properties throughout the component, reducing the stress concentration and failure. So in contrast to the conventional additive manufacturing or conventional multi-material additive manufacturing, which is shape-centric prototyping process, FGM focuses on material-centric prototyping, which gives not only freedom of form, but also the composition and materials freedom, which radically shifts the modeling for additive manufacturing from contour modeling to the performance modeling. So in this modeling technique, the materials information can be allocated inside the design model through voxels, which is the 3D building blocks of the functionally graded additive part, also known as 3D pixel, to capture the information about the object's volume rather than its surface. Thus, multifunctionality is achieved by mapping performance requirements through every voxels while structuring and material allocation of the design part. Functionally graded additive manufacturing shares a lot of advantages of conventional additive technologies, and it also gives the opportunity to control the material deposition and orientation at specific location to achieve the different properties in a single structure. It also gives the greater control in engineered structure, which the other traditional process cannot shows. In classification of FGM, so we can say that FGM can be made of a single material and also the multiple material. The single material FGM is called the homogeneous composition FGM part, which further can be classified according to the porosity gradient and the microstructural gradient. And on the other hand, the heterogeneous composition of the FGM is made of multiple materials, and the gradation is done by chemical composition or multiple phases. When these varied densification, like density gradient and compositional gradient present in a single part, which is called the combined composition FGM. Here we can see the homogeneous composition FGM. So the porosity gradient can brought by gradation, by changing the porosity size and shape, and also the density of the pores throughout the material. And so, which actually which is appreciated by Stephen Keating from MIT researcher team. So he printed concrete which has a radial density variation from hard dense exterior towards the porous core. The density variation along this concrete was achieved at specific location, which actually gives this concrete excellent strength to weight ratio. So thus it makes the concrete lighter, even lighter, but stronger than a solid piece of concrete pillar. In the microstructural gradient, so FGM can offer an isotropic microstructure by changing the process and building parameters with respect to the position of the part. The microstructural gradient can be achieved. So this study shows the microstructural gradient can be achieved by changing the process laser power at different locations in a SLM process of Inconel 718 alloy. The heterogeneous composition of functional graded part can be brought by changing the material composition or the multiple phases created by the materials. So you can see that in this product, the phases, like one phase in another, is mixing in terms of varying the composition, the volume percentage of the reinforcement phase. And this gradation of composition can be done in smoothly throughout the products, and also the stepwise gradation can be achieved. The combined composition is a combination of density variation and also the chemical composition gradient. You can see that there are two multiple materials that are mixed together at different percentage of compositions along the length, and also the porosity distribution was varied throughout the structure. Such kind of combined composition in the nature, such as in animal bones, where the cartilage to bone structure, if you can see that there is elastic and more stiff material is connected to the spongy type of cellular bone tissue. So where different percentage of porosity is distributed along the cross section of the bone. The feature of the gradation, you can change the gradient vector on one-dimensionally or different or throughout the different dimension, uniformly or throughout some special patterns. The FGM process chain consists of mainly three domains, which is the design and modeling domain and the additive manufacturing domain, which is the building part, and followed by the post-processing and quality control. To achieve a successful quality product through this process chain, the design and modeling stage is very important. And the three triptych of this modeling domain, which is the product description and the material allocation and the manufacturing description with the right choice of technology, are need to be optimized for the quality product. So in the design and modeling FGM, so creating a right CAD model with the material gradation and converting all the information to the machine is by appropriate file format is very important. That's why the FGM requires software tools in terms of design and modeling, which can assign the materials or the features of the product at strategic location, and also can analyze the structure along with the material gradation, and also transfer all information to the machine so that it can run the tool path appropriately according to our desired outcome. So similarly, this slide shows you a CAD software tool for FGM production, which has a voxel modeling ability, so which can accumulate different type of soft or hard material, can mix according to the concentration at voxel level, embedded with KA software, which can analyze the building, the solid component with the material gradation information, which gives rise to an optimized 3D model data. For multi-material FDM product, to design in a CAD file, the material allocation is done according to across the voxel and voxel volume, which followed by the transferring the material for the further manufacturing. Here are some voxel modeling software. So some of these are integrated with some specific printer machine, and some is independent. For example, Voxelizer is a control software for a ZMorph VX material extrusion machine, which has a multicolor and multi-material printing feature. On the other hand, Stratasys introduced a GrabCAD voxel modeling software, which can assign the material distribution along a various density and the multiple composition for its Z715 type of machine. So medical researchers can use this technique, this design tool to create this cancellous spongy-like bone anatomical model for the surgical planning very successfully. Hypergenic and Monolith are the independent modeling software, which has the ability to create and the voxel to create the different composition and color according to the at the voxel level. VoxCAD is an open source voxel modeling and analysis software, so which can create the digital model and also can analyze the model along with the gradation of the material successfully. For more information about assigning materials through VoxCAD and material simulation, you can follow the YouTube links here. So the present STL file for additive technology is not sufficient for transferring all material gradation, materials information along with the solid model to the machine. So this enables the development of some new file format, which is suitable for function graded additive manufacturing technique, such as additive manufacturing format, fabricatable voxels, and 3MF. The 7 technologies of additive process can also be utilized to can be utilized to produce FGM part, such as the material extrusion process can produce the function graded part by changing the deposition density and the orientation with a little alteration of the mechanism and feeding system. The another form of material extrusion is called freeze form extrusion, which has the triple feeding mechanism, can carry the paste of the multiple material instead of the filament. And the building process is carried out at the 0 degree centigrade temperature to solidify the green part, followed by the post-processing. This has the ability to print ceramic material. Ceramic function graded additive manufacturing, additive part. Powder bed fusion is spread the powders basically 0.1 millimeter and partially fused by any heating source such as laser, electron beam, selecting it's known as many different process and can also process different materials type. Selective laser sintering has the ability to produce functionally graded additive manufacturing by varying the mechanical properties with correct powder delivery. And it can also process very little powder thickness from 0.02 to 0.05 millimeter thickness, and permitting a very complex structure to be created. The selective laser melting process can fabricate a function graded metallic part where the metal powders are injected into a high power laser beam. So using multiple type of feeding system in SLM process, it can continuously modify the composition of the deposited material and also the density of the deposited powder. Directed energy deposition technique is a well-known technique for repair and also creating part, especially the metallic part. So the laser-based DED technique, which is called laser metal deposition, can deposit function-graded additive part using multiple feeders on a substrate material. Sheet lamination process is a low temperature production process. It also has the ability to create functional part by joining the multiple type of thin metallic foils using ultrasonic welding. And also the FGM FGM can be produced by introducing the intermediate glue layers of different composition. Material jetting or polyjet technology offers the widest range of digital materials with different physical concentration and microstructure. Can be preloaded or pre-configured through the embedded software of the machine. And FGM part can have up to over actually 82 different material properties I showed here, but it can have more than that through material jetting process. Binder jetting process is similar to the powder bed fusion, where the powder powder material is compact and then joined by deposited organic or inorganic binders through selectively through a printer head. But it requires a processing, including sintering or infiltration or curing process. The Z-Corp binder jetting machine can print facial processes using starch powders at different color, using the different color mapping and also the composition and porosity distribution. The special type of vat photopolymerization technique, which is called mask image projection vat photopolymerization technique, can produce FGM part using switchable resin vats for multi-material components and DED and micro mirror device system, which can project the light, the curing light, to the required area, and it has also ability to produce ceramic materials by altering the distribution density variation using the ceramic slurries in the photopolymeric resin. So all 7 standards process can be used for fabrication of functionally graded part, but the key factors of each process are the building parameters. And to get a specific kind of structure of functionally graded part, there are the particular building parameters governs over one another. For example, homogeneous composition is achieved by changing the geometry and material composition. And on the other hand, the microstructural gradient is more influenced by the building strategy. Comparing to the homogeneous, heterogeneous composition material is very difficult. It's complex to achieve because all the building parameters control the outcome a lot. FGM process already shows potential for many novel and existing application, including the aerospace and an automotive, defense, energy, bioimplant, tooling, marine, sports sector as well. This is a very important application of FGM process, multi-material FGM technique, where a hard hydroxyapatite crystallites can be joined together with the soft flexible materials, along with some density variation in the scaffolds of the dental implant. And this is the process chain of this bioadaptable dental implant, which followed reverse engineering approach, and this the whole part cannot be done by following any traditional manufacturing technique. While the FGM process, FGM technology is promising a better solution to many manufacturing industries, but it still has to go further to realize its full potential. And by improving in many aspects of this technology, such as the design guideline, improving the computer-aided software, CAD modeling software, developing the materials allocation strategies and techniques, including new technology concepts, solutions for this technique, and also the post-processing and quality checks. And this is why we are here working together hand in hand in the Ionics Atom platform to share our technological solution and knowledge to the people who can't wait to grow their business along with the technological innovations. Thank you for your attention, and for further question or in his FGM research team. Thank you so much.
Thank you, Isa, for your presentation. I'm not sure that we have any question. I cannot see. No. There is one question. Are currently all these technologies at Brunel University? So probably the question is, currently have all those technologies? Currently using, okay. Are you currently using at your university all the technologies you mentioned in presentation?
No, we don't have. No, we don't have all the technologies to fabricate functional graded part in practical, but we have.
We have
polyjet technology and the material extrusion technology, and we have a design researching in this area. Yeah.
Mm-hmm. Thank you. Part of the answer was not complete because the internet connection is again worse than before, but fortunately so the question is no laser powder bed fusion. You don't have at the...
No, we don't have powder bed fusion. We have polyjet technology and material extrusion and SLM.
Okay, thank you for your answer. And although in agenda we have now plan for have a short break, but Tomislav is already prepared for his last presentation of today's summer school. So I will invite Tomislav to show us how can you design for additive manufacturing by using one of the softwares called Altair. Tomislav, please, can you proceed?
So good afternoon, everyone, and I'm Tomislav Breški. I'm from Faculty of Mechanical Engineering and Naval Architecture here at Zagreb. And so let me share my screen. Today, I'm presenting as a representative from faculty and representative student ambassador from Altair. So we came into contact with Altair through this project, and fortunately they were eager to help us, and they really reached out to us, and they made available everything we needed, and we are now trying to incorporate Altair in our education and in our project work as much as possible. So Altair is for a very long time available on the market with simulation-driven design software, simulations, CFD simulations, and motion simulations, everything else. And lately, they are really one of the strongest ones in the area of additive manufacturing and topology optimization and design for additive manufacturing and so on. So firstly, I would like to thank for everyone from Altair, especially Mr. J.D. Bangal, who helped me prepare this presentation and who helped me with this, I would say, this presentation. So general idea is to show as much as possible mostly interesting applications which were done already as some successful case studies. So here, few of the case studies you probably already saw. So this antenna bracket. So this I thought you didn't. But this is an application of additive manufacturing, but to the extreme. So they've done the case study, they topology optimized the entire injection molding tool. So they didn't produce a hybrid mold, but they produced a mold which was entirely 3D printed and then assembled, and afterwards they tested it with conformal cooling, and it shown some great results. So our goal today is to go through the presentation in the first part, and in the second part I'm going to demonstrate some educational concepts and some features of the Altair Inspire software, which we try to show to our students in, I would say, in elementary courses, so let's say in mechanics, and afterwards we can use them in our classes which are regarded to additive manufacturing. So we are going to cover typical challenges in additive manufacturing. How can we overcome these challenges? By thinking through and by simulating and designing, so we avoid these challenges and issues. And you'll see how Altair, as a software developer, solves these issues. So this, I would say, in industry, if you want to produce something that is durable, you should stick to metal. So this is a general overview of currently, I would say, commercially available additive manufacturing technologies with metal, but selective laser melting and binder jetting, these ones are, I would say, emphasized a bit more, because with them we are striving to serial production. So general idea is to produce parts as quickly as possible with the best material and material properties as possible. So what are the typical challenges while 3D printing metal parts? And you can see here on this fan rotor, you can see that metal 3D printing works like in the way that our parts are welded to the table, and during printing we have residual stresses due to heat, thermal residual stresses, and all these support structures broke during printing because we had too high residual stresses during printing. And that is something which means that these fans aren't at the supposed angle they should be, and generally by looking at this we have a scrap part which we need to print again. As you can see here, this part is relatively big, so we wasted quite a lot of material, and this is something which is avoidable. And how we need to simulate the process, and we need to see how and where the stress concentrations will happen, and then we can try to redesign either the support or redesign the part, which we have to choose which is more acceptable and suitable for our application. So additionally, we can have poor surface quality where overhangs are beyond the threshold. So overhang is angle at which some surface is angled to printing direction. And here you can see that surfaces that are not at a big angle, they aren't angled at excessive angles, they have, I would say, acceptable surface quality. It depends what we want, but let's say this area is not acceptable. It can be solved, so we can eliminate this surface roughness with post-processing, but post-processing is something which makes our supply chain longer. So if we can avoid post-processing, it's something which we want to do. So that is something what we can also eliminate beforehand by simulating the process and seeing what will happen at some certain areas. Snap lines, this happens when also residual stresses during manufacturing, they make some cracks this is welded material, but we know that we here have some stress concentrations. So even though we did the simulation and we designed this part with it, this is the topology optimized part, which you already heard from Axel, but this isn't exactly as the CAD model. So this is produced model, and here we have an issue which we have to solve. Also, we can solve it using software. So as I already mentioned, post-processing is something which is unavoidable, but the general idea is to eliminate it and to make it as easy as possible. And you can see for this bracket that in original, I would say, design, you have a lot of support structures that you have to manually remove them, and that is time consuming, and you can optimize the geometry of support for easier removal, and some surfaces may not need to have support structures, but that is something which we're going to show afterwards. So it's paramount to find a compromise between support removal time and support efficiency. So as people already told today, support in metal is not only regarding positioning of the part, but support here is used for heat dissipation. So we need to have it, but we can minimize its volume by redesigning the part, by making the part orientation during printing a bit different. And here you can see that we need to have some support, but this support is not, it can be eliminated. So what questions do we have to ask ourselves during designing of the part? So first, when we are designing the part, then we need to know for which machine are we designing it. So here at the faculty, we unfortunately don't have additive manufacturing for metals, but fortunately in Croatia, there are few entrepreneurial centers who procure the metal machines, and we have one new institute in Čakovec, and they bought an EOS M290, which is the MLS technology, so selective laser sintering or melting, and so their build volume is 250 by 250 millimeters. So we cannot design a part which doesn't fit into our machine. So this is the first question we have to ask ourselves: where are we going to print it? What are the yearly volumes? So if we need to produce one part, it's not the same if we need to produce 1,000 parts. Maybe it would be usable to use sand printing, so to print some sand cores and to cast parts. So by casting, we can do we can have a much bigger series production, but we can use the topology optimization as a design procedure. Is there a suitable additive manufacturing material? So many metal machines, they don't commercially available metal machines, they might have closed parameters, so you cannot, maybe you can, maybe you can't, select parameters, so you have to stick with material which is available to you. Does the current part have a high tooling cost? So if a part needs to be injection molded, is there a way to redesign it, or is it better to convert to redesign it totally and print it on an HP machine, so on multi-jet fusion? So this is something also which we covered before. Break-even points are the factors which have to be considered during product design. Is there a desire for lightweight performance? So in many applications, weight is a thing which we need to take into account, and if we have the opportunity to reduce weight of our part without sacrificing its performance, why not use it and sell it with a higher added value? Is there an opportunity for part consolidation? So this is also a cool thing you can do, is that if you have a part which consists of 2 or 3 parts, you can redesign it in a way that you incorporate all the functions of these 3 parts, and you incorporate it into a single part, which can then be produced either by additive manufacturing or any other technology which is suitable for production of this part. And also, is there an opportunity for individual customized parts? So many customers, they need, let's say, in medical applications, many parts are patient specific. So by redesigning the part which is specific for application, you need to take into account, you don't need to design it in a way that it is optimized for some high series production. So you need to design it in a way that you can print it without any, I would say, restrictions. So what do we have to take into account? So we need to achieve some performance. In Altair Inspire, multi-body simulations are available, so we can have complex assemblies, and we need to redesign only one part of this entire complex assembly. But the forces and boundary conditions are a bigger picture, so we need to take into account contacts and forces how are being distributed during use of this product. As all simulations, all simulations work on the general principle, which is called GIGO, garbage in, garbage out. So if you don't supply the numerical model with the appropriate boundary conditions, appropriate forces, then your results are also inappropriate and bad to the, I would say, to the scale that you get the result, but when you print it out and you put it into real application, then you might have some, I would say, unexpected behavior which your software didn't tell you. So the best approach is to have various load cases. So we want to design it in a way that we never surpass the yield stress of the materials. So then we can apply the superposition of results. So each result can yield one design, and then afterwards we can combine these results in a final design which is going to be manufactured. So Axel already said how the topology optimization works, but I'm going to say it again. So we need to have some boundary conditions, we need to have design space, and by removing or adding or repositioning the material inside the design space, we get the final design which is suitable for, I would say, various types of technologies. So we can machine the parts, we can cast the parts, or we can manufacturing using available additive manufacturing technologies. So by using Altair Inspire platform, it's called platform because Altair Inspire consists of many software, including software which can. So we are focusing on structures, so we are using Altair Inspire, but also are available Altair Inspire Cast, Altair Inspire Form, extrusion of metal, of polymer, injection molding, foaming. So we can design a part, and in certain time we decide that the most suitable production technology is casting. Then we can simulate the casting procedure, and we can see if our design is castable. That is something which is only available through Altair platform, because you can seamlessly switch from one from one software to another, and to use data you achieved from one software and use it in another to see the results. So this project was also presented at the conference in Portorož in September. So this is a design of a disc harrow. So this is a carriage which is welded, and they at Altair, they redesign it for casting. So this part is casted. As you can see, this geometry is, I would say, really free form. It's really interesting, but some would say, how can you cast this part? So also by using 3D printing. So they partnered with Voxeljet, and at Voxeljet they have the machine which is called VX4000, which can print molds up to 4 meters of length, and the mold is printed, and afterwards they poured the molten metal and achieved these results. So initial geometry initial part has 16 meters of welds. So you need to have people who are doing these welds, and you need to have the technology and the equipment and everything else. You can optimize it for casting. So this is for casting, but this cast can be made by manual molding. So we can achieve 35% reduction in cost. But what is the most important thing is that we can increase fatigue performance, which is for, I would say, in agriculture, for disc harrow, it's important that your part isn't susceptible to fatigue and for crack propagation. But if you want to make it as extreme as possible, then you can print the 3D printed form and pour the molten metal inside it, and you get the finished product, which looks extremely nice. So by using 3D printing in casting, you can have increase in lead time reduction of 75%, which is exceptional in today's market. So here we have also one bracket, which is initially made with polyamide with glass fibers. And what has happened, they tried to redesign it in a way that it's printable without any support, and they achieved first SLM series component. So this component is being installed, is being printed on a large scale. So we are getting close to the large scale additive manufacturing with binder jetting technologies, and with this we will in a few I would say years, we will have some parts which are produced on a mass scale using additive manufacturing. In Inspire we can do the 3D printing simulation. What does this mean? It means that design which we can produce, which we designed in Altair Inspire, we can test it out and how this material and how this part is behaving during printing. So there are some commercially available machines and parameters in Altair Inspire. So by this moment, inside Altair Inspire, they have covered manufacturers EOS, Renishaw, and SLM. So fortunately, since we in the future we are going to play with SLM, with EOS M290 machine, we can do this production simulation inside Altair Inspire. So we can orient the part inside the real build volume. We can optimize the orientation, so we reduce the potential use of supports. We can generate the supports with with ease, so we can select what type of supports do we need. Do we need pin supports? Do we need edge supports? Do we need scaffolding supports or anything in this type? Afterwards, we can preview the slices, and we can export part with supports. But the most important thing is that we can do the thermomechanical analysis. So what does this mean? That means that we get the information about the heat stresses and deformations during printing. So these simulations, they tend to last a bit. So you need to have, I would say, a bit strong workstation in order to do these simulations in a relatively short time. But the most important thing is that you get the information of potential points where the issues might occur. So now we are going to see what can we do to alleviate these issues. So this we already saw, and here you can see that these snap lines are already visible during simulation. So during simulation, we see here that we have some residual stresses, which we can easily manipulate. So here we make this geometry a bit wider, and using Inspire, this geometry modification is extremely easy and fast, which I'm going to show live. So here you can see that we can do the nesting, and here we can print this entire build volume of these parts. So now we are going to do to show bracket for the antenna. How can it be designed and how can we optimize the support usage? So initial topology optimization has given this result, which needs a lot of support to be built. So all of this is waste. So what can we do? First, we need to define our load cases. So antenna center of mass is 50 millimeter above the fixation plate, and our boundary conditions is that one load case shouldn't deform the entire part more than 3 millimeter and 4 millimeter in the other direction. We simulate the both connections with the support and define the material of our parts. So stainless steel 304. So if we don't apply any manufacturing conditions, we get the first result, which is visible here. And this result is the result with most needed support. So it weighs, the part weighs 12 kilos and support weighs 5 kilos. You can see here that by simulating this part, we can find critical area with high residual stresses. So we have deformation of 1.5 millimeter, which means that here we might have some cracks during printing. Afterwards, we redesign it, but we add the overhang angle constraint. So by adding the overhang angle constraint, we don't allow any of the surfaces to be angled more than 45 degrees, and with this we achieve geometry which is printable without support. So we already have solved the issue with supports, but with simulation we saw that we have high residual stresses and in the area where the build has started. So it is most probably that during printing this design would snap off the build plate, and in this part would probably deform in this way. So this is something which we have to redesign, and what we do, we make it a bit bigger, and afterwards we have here, but by redesigning we add a little bit of weight, but we don't have issues with residual stresses, and we don't have issues with residual stresses during printing and cooling. So here you can see this is the final part which is produced. Everything is connected to the build plate. We don't have issues, so we need to cut it off and we can install it, and we can use it for what we intend to use it. So this is the finished first part, and now I'm going to show you what can we do and how can we do the topology optimization and redesign in Altair Inspire. Let me change the software. So here you can see this is something what I've done as a project for our students. So here you can see this robotic gripper, which I optimized in Altair Inspire. I optimized it in a way that we come to the stresses, we find forces which are happening in this jaws, which are used for gripping some parts. As you can see, this part has a lot of, this assembly has a lot of parts, and we need to find forces which are happening during exploitation. We can do this by applying joints, couplers, we can define motors, actuators, we define contacts, and final result is this video, which I'm going to show you. And we get the results of entire force distribution, which happens while applying torque to this screw. So we have stepper motor, we have NEMA 27 stepper motor, which has 600 Newton millimeters of torque, and this torque is rotating the screw, and with this we find forces which are applied to this gripper jaw. And this gripper jaw we are going to optimize in using topology optimization in Altair Inspire. So I'm going to return now to Altair Inspire, and here you can see this. So this gripper jaw is simple geometry. We need to partition it. So what is red is the design space. Design space, as Axel already told you, is area which topology optimization is removing the material. What we do, we apply boundary conditions. So these boundary conditions are not same as when doing the multi-body simulation, but for the sake of this demonstration, we applied just simple boundary conditions, which do not represent the actual state of this part. But the most important thing is shape controls. So what do? We can select how can the topology optimization be removing the material. So if we want to, let's say, stamp this material, then we can apply single draw. So this means that the topology optimization shouldn't produce any overhangs in this normal of this surface. If we have split draw, then this is something which could be suitable for casting. So we have two molds, two halves of the mold, and each part of the mold, each side of the mold is also doesn't have overhangs in its half. If we want extrusion, we can use it for extrusion, but extrusion parameter is used if you want to have a single cross section, which is which isn't angled. And this is appropriate for machining. So if we want to machine this on some, I would say, tabletop CNC machine, then we don't want to have angled surfaces here. And by selecting the extrusion constraint, we will have, and this is something which we done because we wanted to print it with an FDM machine without any overhangs. We selected this extrusion parameter, and we can optimize it. So by running the optimization, so we get the result, which we can select which one is the most appropriate for us. So with this result, we think it's okay. So we are trying to, now we're going to redesign it. And how are we going to redesign it? By using polynorbs geometry. So as you already know, this has, so these bodies are not connected to, so we cannot print this. So this is the idea, this is the basis for our design. So we need to use this part and we need to redesign it in order to produce the final part. And Altair Inspire has features for this, which is called polynorbs, and that is something which isn't available on the market anywhere else. And you can achieve extremely good geometries with very short amount of time. So what do? We design flexible geometry, so which we can really easily manipulate just by selecting few cross sections which are defining one polynorb geometry. We can move these geometries as we want. We can change dimensions. So as you can see, this is not parametric, but since we have the necessary material which is needed to carry the actual loads happening, general idea is you just need to be at least of the dimensions which is recommended, but nevertheless, however you design it, you are going to simulate it afterwards, and you are going to check whether your design is good for the intended use. So you're going to do another FEM simulation, and then you will see whether your design is suitable for this. So you saw that it was really easy to create this one member, but we have a lot of members to create, but it really is simple. So we create few members, and then we can create connect these members automatically. And we can, it is depending on the initial geometry, this can be, in some cases, it can be time consuming, but with this, you can achieve geometries which you probably wouldn't get to them by themselves. So you have the result which the simulation has given, and then you design your part to be, I would say, with you design your final part according to the results which the simulation has given you. So here you see that we have smooth geometry, so we don't have any sudden cross-section changes, and we have to further refine it, so we can make it a bit bigger, but that is iterative. So now we would have to do the simulation of this part. So we apply same boundary conditions, same loads to this new design part, and afterwards, if everything is okay, then we select the machine, appropriate machine, which we are going to use, and then we can print it and use for whatever we need. And I think that would be all from my side. If you have some questions, feel free to ask. So I am an Altair ambassador here in Croatia, and I have many other softwares available from Altair on my location, and I have contacts in Altair who can answer you some questions if you have, which I cannot answer now if I won't have the answers now. So I'm waiting for questions.
Thank you very much, Tomislav, for interesting presentation. I think that this design for additive manufacturing will be more and more important with the future applications because of the optimization of the material consumption, performance of the parts, and so on. Therefore, we will see more and more such designs that are optimized for additive manufacturing and that cannot be produced with any other technology. Do we have a question? At least one for Tomislav? As I can see, there is no question. So as we have questions and answers after each presentation, which is much better because you don't have to take on your mind a question all day to put it at the end of the day. I think that we finish today's summer school with very interesting presentations from field of design for additive manufacturing, advanced application of additive manufacturing, materials, and of course standardization. And if there is no further question, I would like to thank you to all participants and most of all to all presenters who prepare and present today's presentations and also answer on the questions. Again, if someone will need a presentation or all presentations or some particularly a presentation from today's summer school, please contact me at my email and I will send it to you. Thank you once again and have a nice day. Bye.
Thank you, Damer.
Bye to everyone. Bye.